Imagine life not on a planet, but aboard a giant cosmic snowball, hurtling through space at incredible speeds. Picture waking up each morning in a home built into the icy surface of a comet, watching the sun grow brighter and dimmer as your entire world follows its ancient orbital dance. Could humans ever build a permanent civilization on such a wandering celestial body? And what would that truly mean for our species? This isn't just science fiction anymore. As we stand on the brink of becoming a spacefaring civilization, we're forced to consider all possible homes among the stars. We've dreamed of Mars colonies and lunar bases, but what about the thousands of comets that sweep through our solar system? These ancient travelers have been journeying through space since the birth of our solar system 4.6 billion years ago, carrying with them the frozen remnants of the cosmic cloud that formed our sun and planets. The idea might sound impossible at first. After all, comets are icy, dusty objects following highly elliptical paths around the sun. They're not stable like planets or moons. They don't have thick atmospheres or steady climates. But they do have something incredibly valuable: water ice, lots of it. And in the harsh environment of space, water is more precious than gold. Building a civilization on such an object would pose unique and extreme challenges, unlike anything humanity has ever faced. We're talking about creating a home on something that spends years in the frigid outer reaches of the solar system, then swings close to the sun where temperatures soar and the surface erupts in violent jets of gas and dust. It's like trying to build a city on a mountain that's also a time bomb, set to go off every few decades or centuries. But here's the fascinating part. The more we learn about comets through space missions and telescopic observations, the more we realize they might not be as impossible to live on as we once thought. Recent missions have revealed that comets are far more complex and resource-rich than simple dirty snowballs. They contain organic compounds, the building blocks of life itself. They have relatively solid cores beneath their icy exteriors. And most importantly, they're accessible with current or near-future technology. The question isn't just whether we could survive on a comet, it's whether we could thrive there. Could we harness their resources? Could we adapt to their strange cycles? Could we build something permanent and sustainable? Or would it always be a temporary scientific outpost? And perhaps most intriguingly, what would living on a wandering world do to us as a species? To answer these questions, we need to dive deep into the science of comets themselves. We need to understand what we'd actually be building upon, because the reality of comets is far stranger and more complex than most people realize. First, we must understand what exactly we'd be building upon. When most people think of comets, they picture a bright streak across the night sky, a tail of light stretching millions of kilometers behind a glowing head. This dramatic appearance has captivated humanity for millennia, inspiring everything from ancient prophecies to modern scientific missions. But the reality of what comets actually are is far more complex and fascinating than their brief appearances in our skies might suggest. At their core, comets are ancient time capsules, frozen remnants from the very formation of our solar system 4.6 billion years ago. They're like cosmic libraries, preserving the original materials that existed in the primordial disk of gas and dust that eventually became our sun and planets. When we talk about building a civilization on a comet, we're essentially talking about making a home on one of the oldest objects in our cosmic neighborhood. The composition of comets is what makes them both challenging and potentially valuable as human habitats. Contrary to popular belief, comets aren't just balls of ice floating through space. They're complex mixtures of materials that tell the story of our solar system's birth. The primary component is water ice, making up roughly 60 to 80% of most comets. This isn't the clear, pure ice you might find in your freezer. It's dirty ice, mixed with dust particles, rocky debris, and a cocktail of other frozen substances. But water ice is just the beginning. Comets also contain significant amounts of carbon dioxide ice, methane ice, and ammonia ice. These frozen gases are what create the spectacular tails we see when comets approach the sun. As the comet heats up, these ices don't melt like water on Earth. They sublimate, transforming directly from solid to gas and creating the characteristic coma and tail that make comets so visible and beautiful. The rocky and dusty components of comets are equally important for anyone considering them as potential homes. These materials include silicate minerals similar to what we find on Earth, as well as more exotic compounds. Recent missions have detected the presence of complex organic molecules, the carbon-based compounds that are the building blocks of life as we know it. We're talking about amino acids, the components of proteins, and other prebiotic chemicals that might have played a role in the origin of life on Earth. The size of comets varies dramatically, and this variation would be crucial for any civilization planning exercise. The smallest comets might be only a few hundred meters across, essentially cosmic pebbles that would offer little room for human habitation. These tiny wanderers would barely have enough material to build a small research station, let alone a thriving community. On the other end of the spectrum, we have comet giants that can stretch tens of kilometers in diameter. Comet Hale-Bopp, which graced our skies in 1997, has a nucleus estimated to be between 40 and 80 kilometers across. That's roughly the size of a small country, offering potentially vast amounts of space and resources for human development. Imagine trying to explore and utilize an area the size of Luxembourg or Rhode Island, but made entirely of ice, rock, and organic compounds floating through the vacuum of space. The structure of comets is another critical factor that would affect any construction efforts. Far from being solid balls of ice, comets have been revealed by space missions to be surprisingly porous and fragile. The Rosetta mission, which spent 2 years studying Comet 67P Churyumov-Gerasimenko, discovered that the comet's nucleus has a density less than half that of water. This means that comets are essentially loose collections of material held together by their own weak gravity, more like cosmic dust bunnies than solid rocks. This porosity creates both opportunities and challenges for potential human inhabitants. On one hand, the loose structure might make it easier to dig tunnels and create underground habitats protected from radiation and the harsh environment of space. The porous nature could also make it easier to extract water and other resources from the comet's interior. On the other hand, this fragility means that any construction would need to be extremely careful not to destabilize the entire structure of the comet. The gravitational environment on a comet would be utterly unlike anything humans have experienced. Even the largest comets have gravitational fields less than 1,000th the strength of Earth's gravity. To put this in perspective, if you weigh 70 kilograms on Earth, you would weigh less than 70 grams on most comets. That's lighter than a typical chocolate bar. This incredibly weak gravity means that a person could literally jump off the surface of a comet and potentially escape into space if they weren't careful. But perhaps the most defining characteristic of comets, and the one that would most dramatically affect any human civilization built upon them, is their orbital behavior. Unlike planets, which follow relatively circular orbits at consistent distances from the Sun, comets follow highly elliptical paths that take them on wild rides through the solar system. Short-period comets, like the famous Halley's Comet, complete their orbits in relatively brief spans of decades to centuries. Halley's Comet, for instance, returns every 76 years, following an elliptical path that takes it from beyond the orbit of Neptune to closer to the Sun than Venus. During this journey, the comet experiences dramatic changes in temperature, radiation levels, and solar heating that would pose enormous challenges for any permanent inhabitants. Long-period comets present even more extreme scenarios. These cosmic wanderers can take thousands, hundreds of thousands, or even millions of years to complete a single orbit. Some come from the Oort cloud, a spherical shell of icy objects that extends nearly halfway to the nearest star. A civilization built on such a comet would experience periods of incredible isolation, spending millennia in the cold, dark outer reaches of the solar system before making a brief, dramatic passage through the inner solar system. The orbital mechanics of comets also mean that their orientation and rotation can be quite chaotic. While planets typically rotate in predictable patterns, comets can tumble through space in complex ways. Some comets have rotation periods measured in hours, creating rapid day-night cycles. Others rotate much more slowly, leading to extended periods of light and darkness that could last for days or weeks. Understanding these fundamental characteristics of comets is essential because they would shape every aspect of life for any human civilization attempting to make these cosmic wanderers their home. The abundance of water ice offers the promise of a crucial resource for life support, fuel production, and radiation shielding. The presence of organic compounds hints at the possibility of synthesizing food or other biological materials. The porous structure might facilitate construction and resource extraction. However, the weak gravity, extreme orbital variations, and fundamental instability of comets also present challenges that would require revolutionary advances in engineering, life support systems, and human adaptation. Any civilization on a comet would need to be prepared for dramatic changes in their environment, as their entire world swings between the frigid outer solar system and the blazing heat near the sun. The magnetic properties of comets add another layer of complexity to our understanding. Unlike Earth, which has a strong magnetic field that protects us from harmful solar radiation, comets have no such protection. However, as comets approach the sun and begin to outgas, they can develop temporary weak magnetic fields created by the interaction between the solar wind and the comet's atmosphere. This phenomenon was observed by the Rosetta mission and represents a fascinating example of how dynamic and changeable comets can be. The seasonal changes that comets experience are unlike anything on Earth. As a comet approaches the sun, different areas of the surface heat up and begin to sublimate. This process isn't uniform across the comet's surface. Some areas remain in shadow and stay frozen, while others face the sun and become geologically active with jets of gas and dust shooting into space. These jets can be powerful enough to actually change the comet's rotation and orbit over time. For any human inhabitants, these seasonal changes would be both spectacular and terrifying. Imagine living in a place where your backyard might suddenly erupt in a geyser of steam and dust, shooting material into space at speeds of hundreds of meters per second. The ground beneath your feet would be constantly shifting as ice sublimates and the surface collapses into newly formed cavities. The chemical complexity of comets continues to surprise scientists. Beyond the basic ices and organic compounds, missions have detected unexpected materials, including metallic particles, complex carbon chains, and even what appear to be amino acid precursors. The Stardust mission, which collected samples from Comet Wild 2, returned materials that showed comets contain high-temperature minerals that could only have formed near the sun, suggesting that comets are mixtures of materials from both the inner and outer solar system. This chemical diversity means that a comet could potentially serve as a cosmic hardware store, providing a wide range of materials for construction and manufacturing. The metallic particles could be extracted and processed into structural materials. The organic compounds could potentially be used in biological life support systems, or even as precursors for pharmaceutical compounds. The various ices could be separated and used for different purposes, from drinking water to rocket fuel. The surface features of comets are equally diverse and would present unique challenges and opportunities for human habitation. Comet surfaces aren't smooth like billiard balls. They're rugged landscapes featuring cliffs, boulders, smooth plains, and active regions where jets of material shoot into space. The Philae lander, which successfully touched down on Comet 67P, revealed a surface covered in organic compounds and featuring terrain that ranges from soft, powdery regions to areas so hard that the lander's drill couldn't penetrate them. Some comets show evidence of layered structures, suggesting they formed through the gradual accumulation of materials over millions of years. These layers could potentially be read like pages in a book, telling the story of conditions in the early solar system. For a scientific civilization, this would make comets invaluable as research stations, providing direct access to pristine samples from the solar system's formation. The thermal properties of comets create another set of considerations for potential inhabitants. Comet surfaces are among the darkest objects in the solar system, reflecting only about 4% of the sunlight that hits them. This means they absorb solar energy very efficiently when near the sun, but they also radiate heat away very quickly. The result is extreme temperature variations that can range from nearly absolute zero in the outer solar system to temperatures hot enough to boil water when close to the sun. These temperature extremes aren't just challenging for human inhabitants, they're actively destructive to the comet itself. The repeated heating and cooling cycles cause thermal stress that can crack and fracture the comet's surface. Over many orbital periods, this process gradually breaks comets apart, which is why we occasionally see comets split into multiple pieces as they approach the sun. The atmosphere, or more accurately the lack thereof, on comets presents both challenges and opportunities. In the outer solar system, comets have essentially no atmosphere at all. As they approach the sun and begin to outgas, they develop temporary atmospheres called comas that can extend for hundreds of thousands of kilometers around the nucleus. These atmospheres are incredibly thin, much thinner than the atmosphere on Mars, but they do provide some minimal protection from radiation and micrometeorites. For human inhabitants, this changing atmospheric situation would require flexible life support systems. During the comet's journey through the outer solar system, any human habitats would need to be completely sealed and self-contained. As the comet approaches the sun and develops its coma, there might be opportunities to harvest some atmospheric gases, but the violent outgassing would also pose serious risks to any surface installations. The communication challenges of living on a comet would be extraordinary. Earth-based mission control would sometimes be able to maintain contact, but during much of the comet's orbit, communication would be impossible or severely limited. The vast distances involved mean that radio signals could take hours or even days to travel between Earth and a comet in the outer solar system. A civilization on a comet would need to be completely self-sufficient, making all critical decisions without any possibility of consulting with Earth. The question isn't just whether we could survive on such a world, but whether we could create something stable and permanent on an object that is, by its very nature, designed to change. These cosmic time capsules have been following their ancient orbital dances for billions of years, and they'll continue long after humanity is gone. The challenge is figuring out how to join that dance without being destroyed by it. Understanding the true nature of comets reveals both the immense challenges and the tantalizing possibilities they represent. They're not just dirty snowballs, they're complex, dynamic worlds carrying the raw materials of life itself through the cosmos. They're natural spaceships that have been voyaging between the stars since before Earth even existed. The question is whether we're clever enough and brave enough to climb aboard. To live on a comet, we'd first have to reach and land safely. The dream of landing on a comet isn't just science fiction anymore. On November 12th, 2014, humanity achieved something that would have seemed impossible just decades earlier. The European Space Agency's Philae lander successfully touched down on the surface of Comet 67 P. Churyumov-Gerasimenko, becoming the first human-made object to soft land on a comet nucleus. This historic achievement proved that landing on a comet is not only possible, it's something we can do with current technology. But landing a small robotic probe is vastly different from establishing a permanent human settlement. The Philae mission, while groundbreaking, also revealed just how challenging and unpredictable comet landings can be. The lander was supposed to fire harpoons to anchor itself to the surface, but the harpoons failed to deploy. Instead of staying put, Philae bounced twice across the comet's surface in the incredibly weak gravity before finally coming to rest in the shadow of a cliff, where it couldn't receive enough sunlight to power its systems effectively. This bouncing landing illustrates one of the fundamental challenges of building on a comet. The gravitational field is so weak that even the gentlest landing can send objects ricocheting across the surface like a stone skipping across water. On Earth, when you drop something, it falls down and stays down. On a comet, dropped objects can bounce for kilometers before finally settling, and even then, they might not stay settled for long. The extremely low gravity, typically less than 1/1000th of Earth's gravitational pull, means that any construction project would need to completely rethink basic assumptions about how things work. Traditional construction techniques that rely on gravity to keep materials in place simply won't function. Instead, everything would need to be anchored, tethered, or somehow mechanically fastened to prevent it from floating away into space. Consider the challenge of something as simple as pouring concrete for a foundation. On Earth, concrete stays where you pour it because gravity pulls it down and keeps it in place while it cures. On a comet, concrete would immediately float away in all directions unless it was contained. Even if you could contain it, the curing process would be completely different in the vacuum of space and extreme cold. Traditional construction materials and methods would need to be completely reimagined. The surface composition of comets presents another set of engineering challenges. The Rosetta mission revealed that Comet 67P has a surface that varies dramatically from region to region. Some areas are covered in fine dust that could be several meters deep, while others feature exposed ice as hard as rock. Some regions are smooth and relatively flat, while others are dominated by towering cliffs and deep crevasses that could swallow entire buildings. This variability means that any construction project would require extensive geological surveys to understand the local conditions. Unlike building on Earth, where soil conditions might vary gradually across a construction site, comet surfaces can change dramatically over distances of just a few meters. A foundation that works perfectly in one location might be completely inadequate just a short distance away. The porous, fragile nature of comet nuclei creates both opportunities and dangers for construction. The low density and loose structure might make it easier to dig tunnels and underground chambers, which would be essential for protection from radiation and the harsh space environment. However, this same fragility means that construction activities could potentially destabilize large sections of the comet, causing catastrophic collapses, or even breaking the comet apart entirely. Anchoring systems would be absolutely critical for any permanent structures on a comet. Traditional foundations that rely on the weight of a building to keep it stable won't work when both the building and the ground beneath it have virtually no weight. Instead, structures would need to be actively anchored deep into the comet's interior, possibly using systems similar to the ice screws and anchors used by mountain climbers on Earth's glaciers, but adapted for the unique conditions of space. The anchoring challenge becomes even more complex when you consider that comets are constantly changing. As they orbit the Sun, different regions heat up and cool down, causing the ice to sublimate and the surface to shift and collapse. An anchor point that seems solid when the comet is far from the Sun might completely disappear when the comet approaches perihelion, and that section of the surface begins to outgas violently. Power tools and construction equipment would face unique challenges in the comet environment. Electric motors and hydraulic systems might function, but they would need to be specially designed to operate in the vacuum of space and extreme cold. Combustion engines are completely out of the question, since there's no oxygen in the comet's vacuum environment. Solar panels could provide power when the comet is relatively close to the sun, but would be useless during the long periods when the comet is in the outer solar system. The construction timeline would be unlike anything attempted on Earth. Projects would need to be carefully planned around the comet's orbital period, taking advantage of the relatively stable conditions when the comet is far from the sun to do major construction work. As the comet approaches the sun and becomes geologically active, construction crews might need to suspend operations entirely or retreat to underground shelters to avoid the violent outgassing and surface changes. Transportation of materials and equipment to a comet presents its own set of challenges. Unlike Mars or the Moon, which follow predictable orbits that allow for regular launch windows, comets follow highly elliptical paths that might only bring them close to Earth once every few decades or centuries. This means that any major construction project would need to be almost entirely self-sufficient, unable to rely on regular supply missions from Earth. The construction materials themselves would likely need to come primarily from the comet itself. This would require developing entirely new techniques for processing comet materials into usable building supplies. Water ice could potentially be melted and refrozen into structural elements, but the process would need to work in vacuum conditions at extremely low temperatures. The organic compounds found in comets might be processed into plastic, like materials, but again, the manufacturing processes would need to be completely redesigned for the space environment. One of the most promising approaches for comet construction might be to build primarily underground or inside the comet itself. The process would be similar to ice mining on Earth, but adapted for zero gravity and vacuum conditions. Tunnels could be carved into the comet's interior using heated tools that melt and vaporize the ice, creating chambers that could then be lined with more durable materials. Underground construction would provide several crucial advantages. The ice and rock above would provide natural radiation shielding, protecting inhabitants from the cosmic rays and solar radiation that pose serious health risks in space. The underground environment would also be more stable, protected from the violent outgassing and surface changes that occur when the comet approaches the sun. However, underground construction on a comet would also face unique challenges. The porous, fragile structure of comet nuclei means that large underground chambers might not be structurally stable without extensive reinforcement. The sublimation of ice as the comet heats up could cause underground chambers to shift, crack, or collapse entirely. Any underground habitat would need to be designed to handle these dynamic conditions. The construction crew itself would face extraordinary challenges. Working in essentially zero gravity while wearing bulky spacesuits would make even simple tasks incredibly difficult and time-consuming. Tools and materials would constantly try to float away. Without gravity to provide stability, workers would need to be constantly tethered and would need to develop entirely new techniques for manipulating objects and performing construction tasks. The psychological challenges of construction work on a comet should not be underestimated. The worksite would be one of the most isolated and alien environments humans have ever attempted to work in. The comet's surface would be a landscape of ice and rock under a black sky filled with stars, with the sun appearing as nothing more than a bright star in the distance for much of the orbital period. The complete absence of familiar environmental cues like weather, seasons, or even a normal day-night cycle could have profound psychological effects on the construction crew. Safety protocols for comet construction would need to be unlike anything developed for Earth-based projects. The primary danger wouldn't be falling from height, since the weak gravity means that falls are unlikely to be fatal. Instead, the main risks would be floating away from the worksite into space, equipment failures in the vacuum environment, and the unpredictable geological activity as the comet approaches the sun. Emergency procedures would be particularly challenging. On Earth, if something goes wrong at a construction site, help can usually arrive within minutes or hours. On a comet, the construction crew would be completely on their own, possibly for years at a time. Every possible emergency scenario would need to be planned for in advance, with backup systems and redundant safety measures built into every aspect of the construction process. Despite all these challenges, the Philae mission proved that precision landing on a comet is achievable, even if the results aren't always exactly as planned. The Rosetta mission spent 2 years studying Comet 67P in unprecedented detail, mapping its surface, analyzing its composition, and observing its behavior as it approached and receded from the Sun. This wealth of data provides the foundation for understanding what would be required to build permanent structures on a comet. More recent missions have continued to advance our capabilities. NASA's Deep Impact mission successfully impacted Comet Tempel 1, demonstrating that we can not only reach comets, but can also deliberately alter their surfaces. The DART mission showed that we can change the trajectory of small bodies in space, proving that we have the precision and power needed for major engineering projects on comets. The engineering challenges of building on a comet are immense, but they're not insurmountable. They would require developing entirely new construction techniques, materials, and safety protocols. They would demand unprecedented levels of self-sufficiency and advanced planning. Most importantly, they would require accepting that any structures built on a comet would need to be designed to handle constant change and instability. The question isn't whether we have the technical capability to build on a comet. The Philae landing proved that we can reach these cosmic wanderers and place equipment on their surfaces. The question is whether we can develop the engineering expertise and technological innovations needed to build something permanent and livable in such an extreme and dynamic environment. Once anchored, could we find resources to sustain life? The key to any sustainable human settlement beyond Earth lies in the ability to live off the land, or in this case, live off the comet. The concept of in situ resource utilization, or ISRU, has become central to space exploration planning. Instead of shipping everything from Earth at enormous cost and complexity, successful space colonies must learn to harvest and process local materials to meet their basic needs. The question for comet civilizations is whether these ancient cosmic wanderers contain enough useful resources to sustain human life, and whether we can extract and process those resources in the harsh environment of space. The good news is that comets are essentially flying resource depots, packed with some of the most valuable materials for space colonization. The most precious of these resources is water, which makes up 60 to 80% of most comets by mass. To understand why this is so valuable, consider that water isn't just essential for drinking and growing food. In space, water becomes a multi-purpose resource that can be split into hydrogen and oxygen through electrolysis, providing breathable air and rocket fuel. It can also serve as radiation shielding when frozen, and as a heat transfer medium for thermal management systems. The abundance of water on comets is staggering. A typical kilometer-sized comet nucleus contains roughly 1 billion tons of water ice. To put this in perspective, that's enough water to supply a city of 1 million people for about 3,000 years, even accounting for all their industrial and agricultural needs. For a space-based civilization, this represents an almost inexhaustible supply of the most critical resource for human survival. But extracting this water presents unique challenges. Unlike water on Earth, which exists as liquid that can be pumped and processed using familiar techniques, comet water is frozen solid at temperatures that can reach -200 degrees Celsius or colder. The extraction process would need to work by sublimation, heating the ice until it transforms directly from solid to vapor, then capturing and condensing that vapor back into liquid water. The heating process itself presents engineering challenges. Traditional heating methods that rely on combustion won't work in the vacuum of space. Electric heating elements could work, but they would require substantial power supplies. Solar heating might be possible when the comet is relatively close to the sun, but would be useless during the long periods when the comet is in the outer solar system, where sunlight is too weak to provide meaningful energy. One promising approach might be to use focused solar reflectors or even nuclear-powered heating systems to create localized hotspots that could sublimate water ice on demand. The process would need to be carefully controlled to avoid creating uncontrolled outgassing that could destabilize the comet's surface or damage extraction equipment. The extracted water vapor would need to be captured immediately before it escapes into space, requiring sophisticated collection and condensation systems. The purity of comet water adds another layer of complexity to the extraction process. Comet ice isn't pure water like you might find in your freezer. It's mixed with dust, organic compounds, and other frozen materials that would need to be separated out before the water could be used for drinking or life support systems. This contamination isn't necessarily a problem. In fact, some of the contaminants might be valuable resources in their own right, but it does mean that any water processing system would need to include purification and separation capabilities. Beyond water, comets contain other frozen gases that could be extremely valuable for space colonization. Carbon dioxide makes up a significant portion of many comets and could be extracted and used for plant growth in hydroponic systems. On Earth, plants need carbon dioxide for photosynthesis, and space-based agriculture would require a steady supply of CO2 to maintain productive growing systems. The carbon dioxide could also be processed into carbon monoxide and oxygen, providing additional life support options. Methane ice, another common component of comets, represents a potential fuel source. Methane can be burned with oxygen to produce energy, making it valuable for power generation or rocket propulsion. The challenge would be extracting and storing methane in the vacuum and extreme cold of space. But the technology for handling cryogenic gases already exists and could be adapted for comet operations. Ammonia ice, found in many comets, could be processed into nitrogen, which is essential for creating breathable air. Earth's atmosphere is roughly 78% nitrogen, and any space-based life support system would need to replicate this mixture. Ammonia could also be used directly as a refrigerant in cooling systems or processed into fertilizer for agricultural operations. The organic compounds found in comets represent perhaps the most intriguing resource potential. These carbon-based molecules include some of the fundamental building blocks of life, including amino acids, which are the components of proteins. The Stardust mission, which collected samples from Comet Wild 2, identified glycine, the simplest amino acid, along with other complex organic molecules. These organic compounds could potentially be processed into food supplements, or even used as feedstock for biological systems that could produce more complex foods. While a comet civilization probably couldn't survive entirely on processed organic compounds from their host comet, these materials could supplement other food production systems and provide essential nutrients that might be difficult to produce through other means. The mineral content of comets adds another dimension to their resource potential. While comets are primarily ice and organic compounds, they also contain rocky and metallic materials that were incorporated during their formation in the early solar system. These materials include silicate minerals similar to those found on Earth, as well as metallic particles containing iron, nickel, and other elements essential for manufacturing and construction. Extracting and processing these mineral resources would require sophisticated mining and refining operations adapted for the space environment. The techniques would be similar to those being developed for asteroid mining, but adapted for the unique conditions of comets. The low gravity and porous structure of comets might actually make mineral extraction easier in some ways, since there would be less structural integrity to overcome when digging or drilling. The energy requirements for resource extraction and processing on a comet would be substantial and would need to be carefully planned around the comet's orbital cycle. When the comet is close to the Sun, Solar power could provide significant energy for extraction and processing operations. Solar panels could be deployed on the comet's surface or in orbit around the comet to capture sunlight and convert it to electricity. However, during the long periods when the comet is in the outer solar system, solar energy would be virtually useless. At the distance of Jupiter, sunlight is 25 times weaker than at Earth's orbit. Beyond Saturn, solar panels become completely impractical for providing meaningful amounts of power. This means that any resource extraction operation would need alternative power sources for the majority of the comet's orbital period. Nuclear power represents the most likely solution for providing consistent energy throughout the comet's orbit. Small modular reactors could provide steady power, regardless of the comet's distance from the Sun. The challenge would be transporting nuclear fuel to the comet and safely operating nuclear systems in the isolated environment of space. The nuclear reactors would also need to be designed to handle the extreme temperature variations and potential structural instability of the comet environment. Food production on a comet would require creating entirely artificial ecosystems within pressurized habitats. While the comet could provide water, carbon dioxide, and some organic compounds, the actual growing of food would need to happen in carefully controlled environments protected from the vacuum of space and extreme cold. Hydroponic and aeroponic growing systems would be essential, using nutrient solutions that could be partially derived from processed comet materials. The growing systems would need to be completely closed loop, recycling all water and nutrients with minimal waste. Every gram of material would be precious in the isolated environment of a comet, making efficiency and recycling critical for long-term sustainability. The growing chambers would also need to provide artificial lighting, since natural sunlight would be unavailable for much of the comet's orbit. Atmospheric processing and life support systems would need to create and maintain breathable air using materials extracted from the comet. The basic process would involve electrolyzing water to produce oxygen and hydrogen, processing ammonia or other nitrogen compounds to provide nitrogen for the atmosphere, and managing carbon dioxide levels to maintain a breathable mixture similar to Earth's atmosphere. The life support systems would need to handle not just the initial creation of breathable air, but also the ongoing maintenance and recycling of the atmosphere. Humans consume oxygen and produce carbon dioxide, and any sustainable system would need to process these waste gases and regenerate fresh air continuously. The carbon dioxide could be captured and used for plant growth, creating a closed-loop system that maximizes efficiency. Waste processing and recycling would be absolutely critical for comet civilizations. Unlike Earth, where waste can often be disposed of in landfills or natural systems, every material on a comet would need to be recycled and reused. Human waste would need to be processed to recover water and nutrients. Broken equipment would need to be recycled for raw materials. Even the air exhaled by inhabitants would need to be scrubbed and recycled back into the life support system. The manufacturing capabilities needed to process comet resources into useful materials would require sophisticated equipment and expertise. 3D printing and additive manufacturing technologies would be essential for creating tools, spare parts, and even structural components from processed comet materials. The manufacturing systems would need to work with a variety of materials, from processed water ice to refined metals and organic compounds. Quality control and safety systems would be paramount when processing comet resources for human consumption. Unlike resources on Earth, which have been tested and used by humans for thousands of years, comet materials would be completely novel and potentially contain unknown contaminants or toxic compounds. Every batch of processed water, air, or food would need to be thoroughly tested before being introduced into the life support systems. The storage and preservation of processed resources would present unique challenges in the space environment. Water could be stored as ice in naturally refrigerated storage areas, but would need to be protected from sublimation in the vacuum of space. Gases would need to be stored under pressure in specialized containers. Solid materials would need to be protected from thermal cycling and radiation damage. Emergency backup systems would be essential for any resource processing operation on a comet. Equipment failures that might be minor inconveniences on Earth could be life-threatening in the isolated environment of space. Multiple redundant systems would be needed for all critical operations, along with substantial stockpiles of essential resources to handle extended equipment downtime. The seasonal variations in resource availability would require careful planning and management. As the comet approaches the Sun and begins to outgas, some resources might become easier to extract as the ice begins to sublimate naturally. However, the violent geological activity during this period might also make extraction operations dangerous or impossible. Resource extraction would need to be carefully timed to take advantage of favorable conditions while avoiding the most dangerous periods. Despite all these challenges, the abundance of essential resources on comets makes them potentially viable locations for human settlements. The combination of water, organic compounds, minerals, and frozen gases provides most of the raw materials needed to sustain human life. The key challenges are developing the technology and expertise needed to extract and process these resources safely and efficiently in the extreme environment of space. The successful utilization of comet resources would represent a major milestone in humanity's expansion into space. It would prove that we can not only survive in the most remote and challenging environments in our solar system, but that we can thrive there using local resources. The techniques developed for comet resource utilization could also be applied to other space environments, from asteroids to the moons of the outer planets. But beyond resources, a civilization needs stability. Could a comet provide that? Living on a comet would mean accepting that your entire world is fundamentally unstable, constantly changing, and subject to violent transformations that could threaten the survival of any human settlement. Unlike planets or moons, which maintain relatively stable conditions over human timescales, comets are dynamic objects that undergo dramatic metamorphoses as they follow their elliptical orbits around the Sun. Understanding these challenges is crucial for anyone considering the feasibility of comet civilizations. The most dramatic and dangerous aspect of comet life would be the approach to perihelion, the point in the orbit when the comet comes closest to the Sun. During this period, a comet transforms from a quiet, frozen world into an active, potentially violent environment where the surface erupts in jets of gas and dust. The ground shifts and collapses, and the entire structure of the comet can be altered in ways that would be catastrophic for any surface installations. As a comet approaches the Sun, solar heating begins to warm the surface ice, causing it to sublimate directly from solid to gas without melting. This process doesn't happen gradually or uniformly. Instead, it occurs in sudden, violent bursts as pockets of ice reach critical temperatures and explosively convert to vapor. These outbursts can shoot material into space at velocities of hundreds of meters per second, creating spectacular jets that can extend for thousands of kilometers from the comet's surface. For inhabitants of a comet, these jets would represent one of the most serious threats to their survival. Imagine living in a place where the ground beneath your feet could suddenly explode without warning, shooting rocks, ice, and dust into space with the force of a volcanic eruption. The jets don't just pose a direct physical threat to anyone caught in their path. They also gradually erode and reshape the comet's surface, potentially undermining foundations and destabilizing any structures built on the surface. The Rosetta mission observed this process in detail on Comet 67, P. Churyumov-Gerasimenko, documenting how the comet's activity increased dramatically as it approached the Sun. What had been a relatively quiet, stable world became a dynamic environment where new jets appeared regularly. Existing surface features changed or disappeared entirely, and the comet lost millions of tons of material to space. The mission observed boulders the size of houses being moved by outgassing activity, cliffs collapsing as their foundations were undermined by sublimation, and entirely new landscapes being carved by the erosive force of escaping gases. The thermal stresses experienced by comets during their orbital cycles would create constant challenges for any human habitation. As a comet swings from the frigid outer solar system to the blazing heat near the Sun, different parts of the surface experience extreme temperature variations. Areas facing the Sun can reach temperatures well above the freezing point of water, while areas in shadow remain at temperatures approaching absolute zero. These temperature differences create powerful thermal gradients that cause the comet's material to expand and contract at different rates. The result is a constant process of cracking, fracturing, and structural failure as the comet's ice and rock components respond to the changing thermal conditions. For any human structures, this would mean dealing with a foundation that is literally tearing itself apart on a regular basis. The changes aren't just surface phenomena. The heating and cooling cycles affect the entire structure of the comet, potentially causing deep internal fractures and instabilities. Some comets have been observed to split apart entirely during close approaches to the Sun, breaking into multiple fragments that then follow separate orbits. For a civilization built on such a comet, this kind of catastrophic breakup would mean the complete destruction of their world. The radiation environment around comets presents another set of serious challenges for human inhabitants. Unlike Earth, which is protected by its magnetic field and thick atmosphere, comets offer no natural protection from the harmful radiation that pervades space. Cosmic rays, high-energy particles from deep space, constantly bombard the comet's surface with radiation levels that would be lethal to unprotected humans within days or weeks. The situation becomes even more dangerous when comets approach the Sun and enter regions of intense solar radiation. Solar flares and coronal mass ejections can create radiation storms that would be deadly to anyone caught on the surface without adequate shielding. The thin, temporary atmosphere that comets develop near the Sun provides virtually no protection from these radiation hazards. The dynamic nature of the comet's orbit means that radiation exposure would vary dramatically throughout the orbital cycle. During the long periods when the comet is in the outer solar system, cosmic ray exposure would be the primary concern. As the comet approaches the Sun, solar radiation would become increasingly dangerous, potentially requiring inhabitants to retreat to heavily shielded underground bunkers during the most hazardous periods. The gravitational instability of comets creates ongoing challenges for any attempt to establish permanent structures. The extremely weak gravity, combined with the constant loss of material through outgassing, means that the comet's gravitational field is constantly changing. Objects that seem securely anchored at one point in the orbit might become unstable as the comet loses mass and its gravitational field weakens. This gravitational instability is compounded by the fact that comets are not solid objects, but rather loose collections of ice, dust, and rock, held together by weak gravitational forces. The structural integrity of the entire comet depends on this delicate balance, and significant changes in mass distribution caused by uneven heating, outgassing, or human construction activities could potentially destabilize large sections of the comet or even cause it to break apart entirely. The atmospheric conditions around comets create additional complications for human habitation. Unlike planets with stable atmospheres, comets develop temporary, highly variable atmospheric envelopes that change dramatically as conditions change. When far from the Sun, comets have essentially no atmosphere at all, just the hard vacuum of space. As they approach the Sun and begin to outgas, they develop comas that can extend for hundreds of thousands of kilometers, but are still incredibly thin by Earth standards. These temporary atmospheres are not only too thin to breathe, they're also highly toxic, containing carbon monoxide, hydrogen cyanide, and other compounds that would be deadly to humans, even in small concentrations. Any life support system would need to be completely sealed from the external environment, unable to take advantage of any atmospheric resources that might temporarily exist around the comet. The dust environment around active comets would pose serious challenges for equipment and human health. As comets approach the Sun and begin to outgas, they release enormous quantities of fine dust particles that create thick clouds around the nucleus. This dust isn't like household dust on Earth. It consists of microscopic particles of rock, ice, and organic compounds that could damage sensitive equipment and pose serious health risks if inhaled. The dust particles can carry electric charges, potentially causing static electricity problems for electronic equipment. They can also accumulate on solar panels, reducing their efficiency just when solar power becomes most available near the Sun. For humans, the dust could cause respiratory problems, similar to those experienced by astronauts exposed to lunar dust, but potentially more severe due to the chemical composition of comet dust. The communication challenges posed by comet orbits would create serious safety and logistical problems for any human settlement. During much of their orbit, comets are so far from Earth that radio communications would take hours or days to travel between the two locations. This means that any emergency situation would need to be handled entirely by the comet's inhabitants, with no possibility of receiving advice or assistance from Earth. The communication delays also make it impossible to operate equipment on comets remotely from Earth, as is sometimes done with Mars rovers or lunar equipment. Every decision would need to be made locally, requiring comet inhabitants to have expertise in all aspects of their technology and life support systems. There would be no calling technical support when critical systems failed. The psychological challenges of living through the extreme environmental changes of a comet's orbit should not be underestimated. Imagine spending years in the cold, dark outer solar system, where the Sun appears as nothing more than a bright star, then gradually experiencing the approach to perihelion as your entire world transforms around you. The quiet, stable environment where you've been living suddenly becomes an active, dangerous place where the ground erupts in geysers and the landscape changes daily. The stress of living with constant environmental instability could have profound effects on the mental health of comet inhabitants. The knowledge that your entire world could potentially break apart or undergo catastrophic changes would create a level of existential anxiety that few humans have ever experienced. Traditional concepts of home and security would be constantly challenged by the reality of living on a fundamentally unstable world. The seasonal cycles of comets are unlike anything experienced on Earth or other planetary bodies. Instead of the familiar yearly cycles we know, comet seasons can last for decades or centuries. A comet might spend 50 years in the quiet, frozen conditions of the outer solar system, then undergo a brief but intense period of activity as it passes through the inner solar system, then return to dormancy for another 50 years. Planning any kind of civilization around such extreme seasonal variations would require unprecedented long-term thinking and preparation. Infrastructure would need to be designed to survive decades of dormancy, followed by years of violent activity. Food production, energy systems, and life support would all need to function through these extreme cycles, with no possibility of resupply or assistance from Earth. The unpredictability of comet behavior adds another layer of challenge to these already extreme conditions. While we understand the basic physics of how comets behave, predicting exactly when and where outbursts will occur, how severe they will be, or what effects they will have on the comet's structure remains extremely difficult. Each comet is unique, with its own composition, structure, and behavioral patterns that can only be fully understood through direct observation over multiple orbital cycles. This unpredictability means that even the best planning and preparation might not be sufficient to handle all the challenges that a comet civilization might face. Inhabitants would need to be prepared for unexpected emergencies, sudden changes in environmental conditions, and the possibility that their carefully planned systems might need to be completely redesigned in response to unforeseen circumstances. The mechanical stresses on any structures built on a comet would be extraordinary. The constant thermal cycling, vibrations from outgassing activity, and structural changes in the comet itself would subject any human-built structures to forces that buildings on Earth never experience. Materials would need to be selected and designed to handle these extreme conditions, with massive safety factors built into every structural element. The maintenance requirements for equipment operating in the comet environment would be enormous. The combination of extreme cold, radiation, thermal cycling, dust contamination, and mechanical stress would cause rapid degradation of any equipment not specifically designed for these conditions. Replacement parts would need to be manufactured locally, since resupply from Earth would be impossible for most of the comet's orbit. Despite all these challenges, it's important to note that humans have already proven capable of surviving and working in some of the most extreme environments imaginable. Antarctic research stations operate for years in isolation, under conditions that would have been considered impossible just a century ago. The International Space Station has maintained continuous human habitation for over 2 decades in the harsh environment of low Earth orbit. Deep-sea research stations operate under pressures and in conditions that are utterly alien to surface-dwelling humans. The challenges of comet habitation are more extreme than any of these environments, but they're not necessarily insurmountable with sufficient technological development and careful planning. The key would be accepting that life on a comet would be fundamentally different from life on any stable world, requiring new approaches to construction, safety, and long-term survival planning. The environmental challenges of comet habitation would push human engineering and adaptability to their absolute limits. Every system would need multiple backups. Every structure would need to be designed for conditions that change constantly. And every inhabitant would need to be prepared for emergencies that could last for years without any possibility of external assistance. Yet these same challenges could become unique opportunities. The extreme challenges of comet environments don't necessarily make human habitation impossible. They simply require revolutionary approaches to engineering and construction that push the boundaries of what we consider feasible. The key insight is that traditional Earth-based engineering solutions won't work on comets, but entirely new approaches specifically designed for dynamic, low-gravity, radiation-intensive environments could potentially succeed where conventional methods would fail. The most promising approach for comet habitation would be subsurface construction, building entire civilizations beneath the comet's surface where the ice and rock provide natural protection from radiation, thermal extremes, and the violent outgassing that occurs during solar approaches. This isn't just about digging simple tunnels. It's about creating sophisticated underground cities that take advantage of the unique properties of comet materials while providing all the life support and living space that humans need. The process of subsurface construction on a comet would be fundamentally different from underground construction on Earth. Instead of excavating through solid rock or soil, construction crews would be working with a mixture of ice, dust, and loose rocky material that has the consistency of dirty snow but the structural properties of concrete when frozen. This material could be carved, melted, and reshaped using heated tools, creating custom chambers and tunnels that perfectly fit the needs of human habitation. The construction process would involve using thermal lances, essentially high-powered heating elements, to melt and vaporize pathways through the comet's interior. The sublimated ice would be captured and condensed, providing water for life support systems while simultaneously creating the living spaces. This approach turns the excavation process into a resource extraction operation, where the act of building the habitat also provides essential materials for survival. The structural engineering for subsurface comet habitats would need to account for the unique properties of the construction material. Comet ice isn't like terrestrial ice that melts at 0 degrees Celsius and refreezes into solid blocks. Comet ice contains impurities and has been subjected to billions of years of thermal cycling that gives it different structural properties. Engineers would need to develop new techniques for reinforcing ice structures, possibly using fiber reinforcement similar to fiberglass, but adapted for the extreme cold and vacuum conditions. One promising approach would be to create composite materials using processed comet ice as a matrix reinforced with metallic fibers extracted from the comet's rocky components. These composites could provide the structural strength needed for large underground chambers while using materials that are readily available on the comet itself. The manufacturing process would need to work in vacuum conditions at extremely low temperatures, requiring completely new industrial techniques. The pressurization systems for underground comet habitats would be critical for human survival, but would need to be designed to work with ice walls that could potentially sublimate if heated too much. The habitats would need to maintain Earth's normal atmospheric pressure while ensuring that the surrounding ice walls remain stable. This might require active cooling systems to keep the walls below sublimation temperature, or the development of sealant systems that could prevent atmospheric gases from escaping through tiny cracks in the ice. Artificial gravity systems would be essential for maintaining human health during long-term comet habitation. The extremely weak natural gravity of comets would cause the same bone density loss, muscle atrophy, and cardiovascular problems that astronauts experience during long-duration spaceflights. Unlike the International Space Station, where crews can return to Earth after 6 months, comet inhabitants might need to live in low-gravity conditions for years or decades. The most practical approach for generating artificial gravity on a comet would be through rotational systems. Large underground chambers could be constructed as rotating habitats, using centrifugal force to simulate Earth-like gravity. The engineering challenges would be substantial, requiring massive rotating mechanisms that could operate reliably for years in the extreme cold and vacuum conditions. The rotation systems would also need to be perfectly balanced to avoid creating vibrations that could destabilize the surrounding ice structure. An alternative approach might be to use linear acceleration systems, essentially underground railways that could provide brief periods of artificial gravity through acceleration and deceleration. Inhabitants could spend part of each day in accelerating vehicles that would provide the gravitational stimulus needed to maintain bone and muscle health. This approach would be more complex to implement, but might be more energy efficient than maintaining large rotating habitats. The life support systems for comet civilizations would need to be completely closed loop, recycling every molecule of air, water, and waste with unprecedented efficiency. Unlike Earth-based systems that can rely on natural processes to handle waste and regenerate resources, comet habitats would be completely isolated from any natural ecosystem. Every breath of air, every drop of water, and every scrap of organic matter would need to be carefully managed and recycled. The atmospheric processing systems would need to handle not just the creation of breathable air, but also the removal of toxic gases that might seep in from the comet's natural outgassing. Carbon monoxide, hydrogen cyanide, and other dangerous compounds are common in comet atmospheres and could pose serious health risks if they accumulated in the habitat. Advanced filtration and scrubbing systems would be essential for maintaining air quality. Water recycling systems on comets could actually be more efficient than those on other space habitats because of the abundant supply of raw water ice. Instead of trying to recycle every drop of water with perfect efficiency, comet habitats could supplement their recycling systems with fresh water extracted from the comet itself. However, this water would need extensive purification to remove the organic compounds and other contaminants that are naturally present in comet ice. The power systems for Comet civilizations would need to function reliably throughout the extreme variations of the comet's orbit. During the long periods in the outer solar system, solar power would be completely inadequate, requiring alternative energy sources. Nuclear power represents the most viable option, but operating nuclear reactors on comets would present unique challenges related to heat dissipation, radiation shielding, and the structural stability of the reactor foundations. Small modular reactors specifically designed for space applications could provide steady power throughout the comet's orbit. These reactors would need to be designed to handle the thermal cycling and mechanical stresses of the comet environment while providing decades of reliable operation without maintenance from Earth. The reactor cooling systems would need to work in vacuum conditions, probably using radiative cooling rather than conventional heat exchangers. During periods when the comet is closer to the Sun, solar power could supplement nuclear systems and provide extra energy for resource extraction and manufacturing operations. Deployable solar arrays could be stored underground during inactive periods and deployed when solar energy becomes available. The solar panels would need to be designed to handle the dust and debris environment around active comets while maximizing energy collection during brief periods of solar availability. The manufacturing capabilities of comet civilizations would need to be essentially complete, able to produce everything from electronic components to complex machinery using materials extracted from the comet itself. This would require sophisticated 3D printing and additive manufacturing systems that could work with a variety of processed comet materials. The manufacturing systems would need to operate in vacuum conditions and handle materials with properties unlike anything used in terrestrial manufacturing. Metal processing on comets would involve extracting and purifying the metallic particles found in comet nuclei. While these metals might only make up a small percentage of the comet's total mass, even a small percentage of a billion-ton comet represents substantial metallic resources. The challenge would be developing extraction and refining processes that work efficiently in the low-gravity, vacuum environment of a comet. Polymer and plastic production could potentially use the organic compounds found naturally in comets as feedstock. The complex carbon chemistry found in comets includes many of the precursor molecules needed for plastic production, though the manufacturing processes would need to be completely redesigned for space conditions. The ability to produce plastics locally would be essential for creating everything from equipment housings to pressure vessels for life support systems. The transportation systems within comet habitats would need to account for the extremely low gravity environment. Traditional elevators and escalators wouldn't work in microgravity, requiring new approaches to moving people and materials through the underground city. Pneumatic tube systems might be effective for transporting small items, while people might move through the habitat using handholds and guide rails, similar to those used on the International Space Station. Emergency systems for comet habitats would need to handle disasters that could range from equipment failures to catastrophic structural collapse if the comet broke apart. Multiple redundant life support systems would be essential, along with emergency shelters that could maintain human life for extended periods if the main habitat systems failed. Unlike emergencies on Earth, where rescue might arrive within hours, comet emergency systems would need to sustain survivors for years until the next supply mission could reach them. The construction timeline for comet civilizations would need to be carefully coordinated with the comet's orbital cycle. Major construction activities would probably need to be scheduled during the quiet periods when the comet is far from the Sun and geologically inactive. As the comet approaches perihelion and becomes active, construction crews might need to retreat to protected underground areas and suspend all major construction activities. The phased construction approach would probably begin with small, temporary shelters that could house initial construction crews while they built larger, more permanent facilities. The first priority would be establishing basic life support systems and emergency shelters, followed by power systems and resource extraction facilities. Only after these critical systems were operational could larger-scale construction of living quarters and community facilities begin. Quality control and safety systems for Comet construction would need to account for the fact that mistakes could be fatal and help might be years away. Every system would need extensive testing and multiple backup options. Construction standards would need to be far more stringent than anything used on Earth, with massive safety factors built into every structural element and life support system. The materials science required for Comet construction would need to address the unique properties of Comet materials and the extreme environmental conditions. New alloys and composite materials would need to be developed that could maintain their properties through the extreme temperature cycling of Comet orbits. Sealants and adhesives would need to work in vacuum conditions at temperatures ranging from near absolute zero to above the boiling point of water. Advanced robotics would be essential for many aspects of Comet construction and maintenance. Robots could perform dangerous construction tasks in areas too hazardous for humans, such as working on the surface during active periods or performing maintenance on systems exposed to high radiation. The robots would need to be designed to operate autonomously for extended periods, since the communication delays with Earth would make remote operation impossible. The integration of all these systems into a functioning Comet civilization would require unprecedented coordination and systems engineering. Unlike Earth-based cities that can rely on external infrastructure and supply chains, Comet habitats would need to be completely self-sufficient while maintaining the complex technological systems needed to sustain human life in one of the most extreme environments imaginable. The economic considerations for Comet civilizations would be unlike anything attempted in human history. The initial investment would be enormous, requiring the transport of massive amounts of equipment and supplies to a target that might only be accessible for brief periods every few decades. The return on investment would need to be calculated over timescales of centuries rather than years, making traditional economic analysis almost meaningless. However, the potential rewards could also be extraordinary. A successful Comet civilization would prove that humans can survive and thrive in the most extreme environments of our solar system. The technologies developed for Comet habitation could be applied to other space environments, opening up possibilities for mining asteroids, establishing bases in the outer solar system, and eventually venturing to other star systems. The engineering challenges of building a civilization on a comet are immense, but they're not necessarily impossible. They would require breakthrough advances in multiple fields, from materials science to life support systems to nuclear engineering. Most importantly, they would require a fundamental shift in how we think about human habitation, moving away from the assumption that we need Earth-like conditions to survive, and embracing the possibilities of creating entirely artificial environments that can sustain human life indefinitely. But how would inhabitants manage the isolation and irregular orbit? The psychological and social challenges of living on a comet would be as formidable as the technical and engineering obstacles, requiring fundamental adaptations to human lifestyle, culture, and mental health management. Unlike any environment humans have ever permanently inhabited, comet civilizations would face temporal and social isolation so extreme that they would need to essentially reinvent what it means to be part of human society. The day-night cycle on a comet bears no resemblance to the 24-hour rhythm that has shaped human biology and culture for millennia. Comet rotation periods can vary wildly, from just a few hours to several Earth days, creating artificial days that could be shorter than a typical work shift or longer than a long weekend. Some comets have complex tumbling motions that create irregular light patterns with no predictable cycle at all. For humans whose circadian rhythms evolved around Earth's steady day-night pattern, these irregular cycles would create constant biological confusion. The human circadian rhythm system is remarkably stubborn, evolved over millions of years to expect roughly 12 hours of light followed by 12 hours of darkness. When this rhythm is disrupted, As anyone who has experienced severe jet lag knows, the effects go far beyond simple tiredness. Disrupted circadian rhythms affect hormone production, immune system function, cognitive performance, and emotional stability. For Comet inhabitants, dealing with rotation periods that might be 6 hours or 60 hours, the biological stress could be severe and constant. Managing these temporal challenges would require sophisticated environmental control systems within the underground habitats. Artificial lighting would need to simulate Earth-normal day-night cycles, regardless of the actual lighting conditions on the comet's surface. These lighting systems would need to provide not just illumination, but the full spectrum of light that human biology requires, including the blue light wavelengths that help regulate circadian rhythms and the seasonal light variations that affect mood and mental health. The lighting infrastructure would be far more complex than simple electric lights. Different areas of the habitat might need different lighting schedules to accommodate people with varying sleep patterns or work requirements. Public areas might maintain a standard Earth time schedule, while private quarters could be customized for individual preferences. The energy requirements for maintaining these artificial light cycles throughout the comet's long orbital period would be substantial, requiring careful integration with the habitat's power systems. The seasonal variations experienced by comet inhabitants would be unlike anything in human experience. Instead of the familiar yearly cycles of Earth, comet seasons could last for decades or centuries. A comet with a 50-year orbital period might spend 40 years in the cold, dark outer solar system, where the sun appears as nothing more than a bright star, followed by a decade of increasing solar heating and geological activity as it approaches perihelion. These extreme seasonal variations would affect every aspect of life in a comet civilization. During the long dark periods, the habitat would be completely dependent on artificial systems for everything from lighting to heating to energy production. The psychological effects of spending decades knowing that your entire world is hurtling through the cold emptiness of space, with the nearest other humans potentially billions of kilometers away, would be profound and unprecedented. The approach to perihelion would bring its own psychological challenges. As the comet begins to warm and become geologically active, inhabitants would need to deal with the knowledge that their world is becoming increasingly unstable and dangerous. The transition from the quiet, predictable environment of the outer solar system to the violent, chaotic conditions near the sun would create enormous stress and anxiety. Planning daily life around the possibility that the ground might erupt in geysers or the entire comet might break apart would require psychological resilience that few humans have ever needed to develop. The isolation experienced by comet civilizations would be more complete than any isolation in human history. Arctic explorers, ocean voyagers, and even astronauts on the International Space Station all maintain some form of regular communication with the outside world. Comet inhabitants would spend years at a time completely cut off from Earth, with radio signals taking hours or days to travel between the two locations when communication is possible at all. During much of the comet's orbit, real-time communication with Earth would be impossible. The vast distances involved mean that a simple conversation would require waiting hours or days for responses. Emergency situations would need to be handled entirely by the comet's inhabitants, with no possibility of receiving advice or assistance from Earth. This level of isolation would require fundamental changes to how human societies organize themselves and make decisions. The social structures of comet civilizations would need to be designed for extreme self-sufficiency and long-term stability. Unlike Earth-based communities that can rely on external support systems and the broader human civilization, comet inhabitants would be entirely dependent on each other for everything from technical expertise to emotional support. Every member of the community would need to be cross-trained in multiple critical skills. since the loss of key personnel through accident or illness could threaten the survival of the entire settlement. The governance systems for Comet civilizations would face unique challenges. Traditional democratic processes that rely on broad participation and external oversight would be difficult to maintain in a small, isolated community where everyone knows everyone else, and personal conflicts could have life or death consequences. The community would need to develop decision-making processes that could handle both routine governance and emergency situations while maintaining social cohesion over periods of decades or centuries. Conflict resolution in Comet civilizations would be critical for long-term survival. In normal human communities, people who can't get along can simply avoid each other or move away. On a comet, the entire human population might consist of fewer people than a typical neighborhood, all living in close quarters with no possibility of escape or outside intervention. The community would need sophisticated systems for preventing and resolving conflicts before they could threaten the social stability essential for survival. The cultural development of Comet civilizations would be fascinating to observe. Cut off from Earth for extended periods, these communities would inevitably develop their own traditions, customs, and ways of life adapted to their unique environment. The shared experience of living through the extreme cycles of comet life would create bonds between community members that no Earth-based human could fully understand. Over generations, comet inhabitants might develop cultural practices and social norms that would seem completely alien to Earth-based humans. The education systems for comet children would need to prepare them for a life completely unlike anything experienced by previous generations of humans. These children would grow up knowing that their entire world is a wandering ball of ice and rock, that the nearest other humans are impossibly far away, and that their survival depends entirely on maintaining complex technological systems in one of the most hostile environments imaginable. The psychological implications of this upbringing are difficult to even imagine. Children born on comets would face unique developmental challenges. The low-gravity environment would affect their physical development in ways that are not yet fully understood. Their social development would occur in the extremely small community of the comet settlement, potentially limiting their exposure to the diversity of human personalities and relationships that Earth-based children experience. Their sense of identity and place in the universe would be fundamentally different from that of any previous generation of humans. The maintenance of human culture and knowledge would be a critical concern for comet civilizations. Cut off from Earth's libraries, universities, and cultural institutions, comet settlements would need to maintain their own repositories of human knowledge and culture. This would require not just digital storage systems, but also the human expertise needed to understand and apply that knowledge. The loss of critical knowledge due to equipment failure or the death of key personnel could set the civilization back by decades or centuries. Entertainment and recreational activities would be essential for maintaining mental health during the long periods of isolation and confinement. Traditional Earth-based recreation that relies on natural environments, large social groups, or external entertainment industries would be impossible on comets. The community would need to develop new forms of entertainment and recreation adapted to their confined environment and limited population. Virtual reality systems could potentially provide some relief from the physical limitations of comet life, allowing inhabitants to experience simulated natural environments or interact with larger virtual communities. However, these systems would need to be designed and maintained entirely within the comet settlement, since downloading new content from Earth would be impossible during most of the orbital period. The work-life balance in comet civilizations would be completely different from anything experienced on Earth. The survival of the community would depend on maintaining complex technological systems that require constant monitoring and maintenance. Unlike Earth-based jobs where people can go home at the end of the day and leave work behind, comet inhabitants would be on call 24 hours a day for critical system failures or emergencies. The psychological stress of this constant responsibility would be enormous. Mental health care would be absolutely critical for Comet civilizations, but would face unique challenges. Traditional therapy and counseling approaches might not be effective for dealing with the unprecedented stresses of Comet life. The small population size would mean that everyone knows everyone else's personal problems, making confidentiality difficult to maintain. The isolation from Earth-based mental health resources would require the community to develop its own expertise in psychology and psychiatry. The medical challenges of long-term isolation would extend beyond mental health to physical health issues that are difficult to treat without access to Earth-based medical facilities. Complex medical procedures, surgical operations, and treatment of serious injuries would need to be handled entirely within the Comet settlement. The community would need medical personnel trained in a wide range of specialties, along with medical equipment and supplies that could handle any health emergency that might arise. The reproductive and family planning considerations for Comet civilizations would involve complex decisions about population growth, genetic diversity, and resource allocation. The limited space and resources of Comet habitats would impose strict limits on population size, requiring careful planning of births and family sizes. The genetic diversity of the founding population would be critical for preventing inbreeding and maintaining healthy populations over multiple generations. Raising children in the extreme environment of a comet would require completely new approaches to childcare and education. Children would need to learn not just academic subjects, but also the technical skills needed to maintain their artificial world. They would need to understand from an early age that their survival depends on technological systems, and that equipment failure could be fatal. This level of responsibility and awareness would create psychological pressures that no Earth-based child has ever experienced. The communication systems within Comet settlements would need to handle not just technical communications, but also the social and emotional needs of the community. With no external social networks or communication systems, the internal communication infrastructure would need to support everything from work coordination to personal relationships to community governance. The design of these systems could have profound effects on how the community develops socially and culturally. The decision-making processes for long-term planning would need to handle timescales that exceed normal human lifespans. Decisions made by the founding generation of a Comet settlement could affect the lives of their great-grandchildren in ways that are difficult to predict or plan for. The community would need governance systems that could handle both immediate survival needs and long-term strategic planning over periods of centuries. The relationship between Comet civilizations and Earth would evolve over time as the settlements became more self-sufficient and developed their own distinct cultures. The initial dependence on Earth for supplies, knowledge and cultural connection would gradually decrease, potentially leading to Comet civilizations that view themselves as independent entities rather than extensions of Earth-based humanity. This cultural evolution could have profound implications for the future of human civilization as a whole. The psychological rewards of Comet life could potentially offset some of the challenges. The inhabitants would be pioneers in the truest sense, exploring and settling one of the most extreme environments humans have ever attempted to inhabit. The sense of accomplishment and purpose that comes from building a sustainable civilization in such impossible conditions could provide powerful motivation for dealing with the isolation and hardships. The scientific opportunities available to Comet inhabitants could also provide intellectual stimulation and purpose that helps offset the psychological challenges. Living on a comet would provide unprecedented opportunities to study these ancient objects and understand the formation of our solar system. The inhabitants would be conducting research that could revolutionize our understanding of the universe, while simultaneously proving that humans can survive in the most extreme environments imaginable. But could this isolated life also open doors to new scientific discoveries? While the challenges of establishing a Comet civilization are immense, the scientific opportunities such a settlement could provide would be equally extraordinary. A permanent human presence on a comet would offer research possibilities that are simply impossible to achieve through robotic missions or Earth-based observations. These scientific opportunities could not only justify the enormous investment required to establish comet settlements, but could also revolutionize our understanding of the solar system's formation, the origin of life, and the possibilities for human expansion into the cosmos. Comets represent some of the most pristine materials available for study in our solar system. Unlike planets and moons, which have been geologically active and have had their original materials mixed, heated, and chemically altered over billions of years, comets have remained largely unchanged since the solar system's formation 4.6 billion years ago. They are essentially cosmic time capsules, preserving samples of the original nebular material from which the Sun and planets formed. A permanent scientific station on a comet would provide unprecedented access to these ancient materials. Instead of relying on tiny samples returned by robotic missions or remote observations through telescopes, comet scientists would have unlimited access to fresh, uncontaminated samples from throughout the comet's interior. They could track how different layers of the comet formed over time, analyze the chemical variations that occurred during the solar system's early development, and potentially discover completely new types of materials that have never been observed before. The drilling and excavation activities required for habitat construction would simultaneously serve as massive geological surveys, revealing the internal structure and composition of the comet in detail that no robotic mission could match. Every tunnel carved for human habitation would expose new cross-sections of ancient ice and rock. Every chamber excavated for living space would provide samples spanning potentially millions of years of the comet's formation history. The organic chemistry research opportunities on comets would be particularly valuable for understanding the origin of life. Comets contain complex organic compounds, including amino acids, the building blocks of proteins, and potentially even more complex prebiotic molecules. Having permanent access to these materials would allow scientists to conduct detailed studies of how organic chemistry might have developed in the early solar system and potentially contributed to the emergence of life on Earth. Laboratory facilities on comets could maintain samples at their natural ultra-cold temperatures, preserving delicate organic molecules that might be destroyed by the heating and contamination that occurs when samples are returned to Earth. Scientists could study the three-dimensional structure of organic compounds as they exist naturally in space, potentially revealing molecular arrangements and chemical processes that have never been observed before. The isotopic composition of comet materials could provide crucial insights into the processes that occurred during the solar system's formation. Different regions of the early solar nebula had different chemical compositions and temperatures, and these variations are preserved in the isotopic ratios of elements found in comets. By analyzing materials from throughout a comet's interior, scientists could essentially read the chemical history of the early solar system like a geological record. The comparative planetology opportunities would be enormous. Different comets formed in different regions of the early solar system and have followed different orbital paths since their formation. A network of scientific stations on multiple comets could provide comparative data about how different regions of the solar system evolved and how different thermal histories affected the preservation of primitive materials. The astronomy and astrophysics research potential of comet-based observatories would be extraordinary. Comets spend most of their time in the outer solar system, far from the light pollution, atmospheric interference, and radio noise that limits Earth-based observations. A telescope system on a comet could achieve observational capabilities that would be impossible from Earth or even from most other space-based platforms. The orbital motion of comets provides natural parallax measurements over enormous baselines. As a comet travels from the outer solar system to the inner solar system and back, it provides observation points separated by billions of kilometers. This vast baseline would allow for precise distance measurements to stars and other celestial objects that are impossible to achieve from Earth's much smaller orbital motion. The extremely cold environment of comets in the outer solar system would be ideal for infrared astronomy. Infrared telescopes need to be cooled to very low temperatures to reduce thermal noise, and the natural deep freeze of comets would provide this cooling without the need for complex and limited refrigeration systems. Infrared observations from comets could detect the heat signatures of planets around other stars, study the formation of stellar systems, and observe the most distant galaxies in the universe. Radio astronomy from comets would be free from the electromagnetic interference that increasingly plagues Earth-based radio telescopes. The isolation of comets would provide a naturally quiet radio environment where sensitive receivers could detect extremely faint signals from distant astronomical sources. The lack of ionosphere and atmospheric interference would allow for radio observations across frequencies that are impossible to observe from Earth. The gravitational wave detection possibilities from comet-based instruments could be revolutionary. The isolation and stability of comet-based platforms, combined with the ability to create very long baseline interferometers between multiple comets, could enable gravitational wave detection with sensitivity far exceeding current Earth-based systems. The natural motion of comets could provide varying orientations and baselines that would allow for detailed characterization of gravitational wave sources. Solar physics research from comets would provide unique perspectives on our star's behavior. Comets travel through different regions of the solar wind and magnetic field, experiencing conditions that range from the intense solar environment near perihelion to the barely detectable solar influence in the outer solar system. Scientists on comets could study how the solar wind evolves as it travels outward from the sun, and how it interacts with the various materials and magnetic fields found throughout the solar system. The study of cosmic rays and space weather from comet platforms would provide insights into some of the most energetic processes in the universe. Cosmic rays, high-energy particles from deep space, interact differently with matter at different distances from the sun and in different magnetic environments. Comet-based detectors could study how cosmic rays change as they penetrate deeper into the solar system and how they interact with the solar magnetic field. Planetary science research would benefit enormously from comet-based observation platforms. The orbital motion of comets provides viewing angles and distances to planets that are impossible to achieve from Earth. During certain parts of their orbits, comets can provide close-up views of the outer planets and their moon systems that would require dedicated space missions to achieve from Earth-based launches. The microgravity research opportunities on comets would be unique in the solar system. Unlike other microgravity environments such as orbiting spacecraft, comets provide a stable platform with minimal vibration or disturbance. This environment would be ideal for studying fluid physics, crystal growth, and biological processes under conditions that cannot be replicated on Earth or in typical spacecraft environments. Materials science research on comets could take advantage of the extreme cold, vacuum, and low-gravity environment to study properties of matter under conditions that are impossible to achieve in Earth-based laboratories. The natural refrigeration provided by comet environments could enable studies of superconductivity, quantum effects, and exotic states of matter that require extremely low temperatures. The life sciences research possibilities on comets would extend far beyond studying comet materials themselves. The extreme environment of comet habitats would provide natural laboratories for studying how life adapts to radiation, low gravity, isolation, and other stresses that would be encountered during long-duration space missions or colonization of other planets. The research conducted on comet-based human settlements could directly inform the design of future space missions and planetary colonies. Astrobiology research on comets could address some of the most fundamental questions about life in the universe. The organic compounds found naturally in comets, combined with the energy sources and chemical processes available in comet environments, could provide insights into how life might arise in other locations throughout the cosmos. Laboratory experiments on comets could test whether the conditions found on these objects could support the development of life or serve as stepping stones for life to spread between planets. The psychological and social sciences research opportunities would be equally valuable. Comet civilizations would represent unprecedented social experiments in human adaptation to extreme environments. Studies of how human societies develop, govern themselves, and maintain culture under conditions of complete isolation would provide insights relevant to future space colonization efforts and potentially to understanding human social development in general. The technology development opportunities on comets would drive innovation in countless fields. The extreme challenges of comet environments would push the boundaries of engineering, materials science, energy systems, life support technology, and manufacturing processes. Technologies developed for comet habitation could have applications in many other extreme environments, from deep ocean exploration to Antarctic research to future space missions. The communications and data transmission research opportunities would be substantial. The extreme distances and communication delays involved in comet operations would drive development of new approaches to data compression, error correction, autonomous systems, and distributed computing. These technologies could have broad applications for Earth-based communications and computing systems. The international cooperation opportunities presented by comet research could have profound benefits for human civilization. The enormous challenges and costs of establishing comet settlements would virtually require international cooperation on a scale that has never been attempted. The shared scientific goals and mutual dependence required for comet operations could serve as models for international cooperation in addressing other global challenges. The education and outreach potential of comet civilizations would be extraordinary. The dramatic nature of living and working on these cosmic wanderers would capture public imagination in ways that could inspire new generations of scientists and engineers. The real-time documentation of life on comets could provide educational content that would make science and space exploration accessible and exciting to people around the world. The economic research opportunities would include studying how human economies develop under conditions of extreme resource scarcity and isolation. Comet settlements would need to develop economic systems that are completely self-sufficient while maintaining technological sophistication. The lessons learned could inform economic theory and provide insights relevant to sustainable development on Earth. The philosophical and ethical research opportunities would address fundamental questions about humanity's place in the universe. Living on comets would force humans to confront questions about what it means to be human when separated from Earth and living in completely artificial environments. The ethical implications of creating human settlements in such extreme environments would require new approaches to bioethics and environmental philosophy. The archive and preservation opportunities would be invaluable for maintaining human knowledge and culture. Comet settlements could serve as backup repositories for human knowledge, literature, and culture, providing protection against catastrophic events that might threaten Earth-based civilization. The extreme isolation and stability of comet environments could make them ideal locations for long-term preservation of critical information. The space exploration research conducted from comet platforms could revolutionize our understanding of the outer solar system and beyond. Comets naturally travel to regions of space that are extremely difficult and expensive to reach with conventional spacecraft. Scientific instruments based on comets could study the outer planets, their moon systems, the Kuiper belt, and potentially even the Oort cloud in ways that would be impossible from Earth-based missions. The fundamental physics research opportunities would take advantage of the unique conditions found on comets to test theories and conduct experiments that are impossible in Earth-based laboratories. The extreme cold, low gravity, and isolation of comet environments could provide natural laboratories for studying quantum mechanics, relativity, and other fundamental aspects of physics under conditions that cannot be replicated elsewhere. Could humans adapt and evolve on comets long-term? The long-term biological and evolutionary implications of establishing permanent human settlements on comets would be profound and largely unprecedented in human history. Unlike previous human migrations to new environments on Earth, comet colonization would expose humans to conditions so radically different from our evolutionary environment that they could potentially drive significant biological adaptations within just a few generations. Understanding these biological challenges and their potential solutions is crucial for assessing the long-term viability of comet civilizations. The most immediate and well-documented biological challenge would be the effects of long-term exposure to microgravity on human physiology. Decades of research on astronauts aboard the International Space Station and previous space missions have revealed that the human body undergoes significant changes when removed from Earth's gravitational environment. These changes affect virtually every system in the body and become more pronounced the longer a person remains in microgravity. Bone density loss represents one of the most serious microgravity health challenges. On Earth, the constant stress of supporting body weight against gravity stimulates bone cells to maintain and rebuild bone tissue. In the minimal gravity of a comet, this stimulus disappears, causing bones to lose calcium and become progressively weaker. Astronauts on the International Space Station lose bone density at rates of 1 to 2% per month, a rate that would lead to severe osteoporosis within just a few years if left unchecked. For permanent comet inhabitants, this bone loss could become catastrophic over time. Without effective countermeasures, first-generation comet colonists might find themselves unable to return to higher gravity environments like Earth or Mars. Their bones could become so fragile that even minor impacts or falls could result in serious fractures. More concerning for long-term colonization, children born and raised in comet gravity might never develop the bone density needed to survive in higher gravity environments. Muscle atrophy presents equally serious challenges for comet inhabitants. Human muscles evolved to work against Earth's gravity, and without that constant resistance, they begin to weaken and shrink within days of entering microgravity. Astronauts on the International Space Station must exercise for several hours each day using specialized equipment to maintain muscle mass. And even with intensive exercise programs, they still experience significant muscle loss during long-duration missions. The cardiovascular system faces unique stresses in microgravity environments. On Earth, the heart must work against gravity to pump blood to the brain and upper body. In microgravity, this workload disappears, causing the heart muscle to weaken over time. Blood distribution also changes, with more blood remaining in the upper body and head, potentially causing vision problems and increased pressure on the brain. These cardiovascular changes could have serious implications for the health and cognitive function of long-term comet inhabitants. The vestibular system, which controls balance and spatial orientation, becomes confused in microgravity environments. Most astronauts experience space sickness during their first few days in orbit, with symptoms similar to severe motion sickness. While most people adapt to microgravity within a few days, the long-term effects of vestibular system disruption are not well understood. For comet inhabitants who might spend their entire lives in microgravity, these effects could be permanent and could affect their ability to function in higher gravity environments. Vision changes, known as spaceflight-associated neuroocular syndrome or SANS, have been observed in astronauts on long-duration missions. The exact mechanisms are not fully understood, but the condition appears to be related to fluid shifts and pressure changes that occur in microgravity. Some astronauts have experienced permanent vision changes after long-duration flights, raising concerns about the long-term visual health of permanent space inhabitants. The immune system appears to be weakened by long-term exposure to microgravity and radiation, making space inhabitants more susceptible to infections and potentially reducing their ability to heal from injuries. The mechanisms behind these immune system changes are complex and not fully understood, but they represent serious concerns for isolated communities that cannot rely on Earth-based medical support. Radiation exposure presents another major biological challenge for Comet inhabitants. Unlike Earth, which is protected by its magnetic field and thick atmosphere, comets offer no natural protection from the cosmic radiation that pervades space. This radiation consists of high-energy particles from deep space and solar radiation that can damage DNA and increase the risk of cancer, genetic mutations, and other health problems. The radiation environment around comets varies dramatically, depending on their location in their orbital cycle. During the long periods when comets are in the outer solar system, cosmic ray exposure is the primary concern. As comets approach the Sun, solar radiation becomes increasingly dangerous, potentially creating radiation storms that could be lethal to unprotected humans. The irregular orbital paths of comets mean that radiation exposure patterns would be unlike anything experienced by life on Earth. Long-term radiation exposure could have genetic consequences that affect not just the original colonists, but their children and future generations. High-energy radiation can cause mutations in reproductive cells, potentially leading to genetic disorders in offspring. The isolated nature of comet communities means that any genetic problems that develop could become amplified over generations due to the limited gene pool of the founding population. The development of effective radiation shielding would be critical for protecting comet inhabitants, but the shielding requirements would be substantial. Water ice, which is abundant on comets, provides effective radiation shielding, but the thickness required for complete protection would make surface activities difficult or impossible during high radiation periods. Underground habitats would provide natural shielding, but inhabitants might need to spend most of their time in heavily protected areas. The psychological and neurological effects of long-term isolation and confinement could have biological consequences that are difficult to predict. Chronic stress, depression, and anxiety can have measurable effects on immune function, hormone production, and overall health. The extreme isolation and environmental stresses of comet life could create psychological conditions that manifest as physical health problems over time. Sleep disorders could become serious health issues for comet inhabitants dealing with irregular day-night cycles and artificial lighting. Disrupted sleep patterns affect hormone production, immune function, and cognitive performance. The artificial nature of comet habitats means that natural light cues would be completely absent, requiring sophisticated environmental control systems to maintain healthy sleep-wake cycles. Nutritional challenges would be significant for comet communities that must produce all their food artificially. The limited variety of foods that could be grown in controlled environments might lead to nutritional deficiencies that could affect health and development over time. Supplements and synthetic nutrients could address some of these issues, but the long-term effects of diets that differ significantly from natural human nutrition are not well understood. Reproductive health and child development in comet environments raise complex questions about the long-term viability of comet civilizations. Pregnancy and fetal development in microgravity environments have never been studied in humans, and animal studies have shown various developmental abnormalities in space conditions. The radiation exposure, artificial atmosphere, and psychological stresses of comet environments could all potentially affect reproductive health and child development. Children born and raised on comets would face unique developmental challenges. Their bones and muscles would develop in microgravity conditions, potentially making them unable to function in higher gravity environments. Their immune systems would develop without exposure to Earth-based pathogens, potentially making them vulnerable to diseases if they ever traveled to other human settlements. Their psychological and social development would occur in the extremely artificial and isolated environment of comet habitats. The genetic diversity of comet populations would be a critical factor in long-term biological viability. Small founding populations are vulnerable to genetic bottlenecks and inbreeding depression, where limited genetic diversity leads to increased rates of genetic disorders and reduced fitness. Comet settlements would need to be founded with careful attention to genetic diversity and might need periodic introduction of new genetic material from Earth or other settlements to maintain healthy populations. Adaptation to comet environments might occur more rapidly than traditional evolutionary timescales would suggest. Some researchers have proposed that the extreme selective pressures of space environments could drive rapid evolutionary changes, potentially leading to human populations that are specifically adapted to space conditions within just a few generations. These adaptations might include improved radiation resistance, better calcium retention in low gravity, or enhanced stress tolerance. However, such rapid adaptation could come at the cost of compatibility with Earth environments. Humans who become well adapted to comet conditions might find it difficult or impossible to return to Earth's higher gravity and different atmospheric conditions. This could lead to the development of distinct human populations that are essentially trapped in their chosen environments. Medical care and life support systems would need to address health challenges that have never been encountered in Earth-based medicine. Comet medical facilities would need to handle everything from routine healthcare to complex surgeries and emergency medicine, all while dealing with the unique physiological effects of the comet environment. Medical personnel would need training in space medicine that goes far beyond current space medical knowledge. Pharmaceutical production on comets would face unique challenges in maintaining drug stability and effectiveness in the extreme cold and radiation environment. Many medications have not been tested for long-term storage in space conditions, and the manufacturing processes for producing medications locally would need to be adapted for comet environments. Artificial gravity systems could potentially address many of the biological challenges of comet habitation, but implementing effective artificial gravity on comets would be technically challenging and energy-intensive. Rotating habitats could provide centrifugal force to simulate gravity, but the engineering requirements for large rotating structures on unstable comet surfaces would be substantial. The biological monitoring and health assessment systems for comet inhabitants would need to track health parameters that are not routinely monitored on Earth. Changes in bone density, muscle mass, cardiovascular function, and radiation exposure would need continuous monitoring to detect health problems before they become serious. This monitoring would require sophisticated medical equipment and expertise that might be challenging to maintain in isolated comet settlements. Genetic engineering and biotechnology could potentially provide solutions to some of the biological challenges of comet habitation. Enhanced radiation resistance, improved bone retention in low gravity, or better adaptation to artificial atmospheres could potentially be achieved through genetic modifications. However, such modifications would raise ethical questions about altering human biology for environmental adaptation. The development of closed-loop ecological systems would be essential for maintaining the biological environment needed for human health. These systems would need to handle not just air and water recycling, but also waste processing, food production, and the maintenance of beneficial microorganisms that are essential for human health. The artificial nature of these ecosystems means that any disruption could have cascading effects on human health. Biomedical research conducted on comet settlements could provide valuable insights into human adaptation to extreme environments. The unique conditions of comet habitation would create natural experiments in human physiology that could advance understanding of space medicine, radiation biology, and human adaptation. This research could inform the design of future space missions and planetary colonies. The long-term biological viability of comet civilizations would depend on successfully addressing all of these challenges through a combination of technology, medical care, and potentially biological adaptation. The success or failure of comet settlements could ultimately determine whether humans can successfully expand beyond Earth to become a truly spacefaring species. The biological considerations for comet civilizations represent some of the most complex and uncertain aspects of human space colonization. While the challenges are substantial, they are not necessarily insurmountable with sufficient technological development and careful planning. The key question is whether humans can maintain their health and biological viability while adapting to environments that are radically different from those in which our species evolved. But why build on a comet when planets or moons seem more practical? After examining all the extreme challenges and biological risks of comet habitation, a reasonable person might wonder why anyone would choose to build a civilization on these wandering ice balls, when seemingly more practical alternatives, like Mars colonies or lunar bases, appear much more achievable. The answer lies in understanding the unique advantages that comets offer, advantages that could make them not just viable alternatives to planetary settlements, but potentially superior choices for certain types of human space colonization. The most compelling advantage of comet civilizations is their fundamental mobility. Unlike planets and moons, which are locked into fixed orbits around the Sun, comets are natural spacecraft that travel throughout the solar system on predictable trajectories. This mobility transforms comets from simple destinations into transportation hubs that could revolutionize how humans explore and settle the solar system. A civilization built on a comet wouldn't just be establishing a single outpost. They would be creating a mobile base that could visit multiple destinations over the course of its orbital journey. Consider the strategic implications of this mobility. A comet with a 50-year orbital period might spend a decade near Jupiter's moons, providing an ideal staging area for exploring Europa, Ganymede, and the other fascinating worlds of the Jovian system. The same comet might then travel to the asteroid belt, offering opportunities to survey and potentially mine numerous asteroids during its passage. Later in its orbit, it might provide close approaches to Saturn, giving inhabitants front-row seats to study the rings and moons of the most spectacular planet in our solar system. This natural mobility could make comet civilizations incredibly valuable as exploration platforms. Instead of launching separate missions to each destination in the outer solar system, a single comet-based expedition could visit multiple targets over the course of its orbit. The comet would provide a stable, well-supplied base of operations that could support extensive exploration activities without the need for complex resupply missions from Earth. The resource advantages of comets are often underestimated when compared to other potential space settlement locations. While Mars and the Moon have received more attention as colonization targets, they both face serious resource limitations that comets could potentially avoid. Mars has limited water in easily accessible forms, and the Moon has virtually no water at all. Comets, by contrast, are essentially flying water reservoirs with billions of tons of easily accessible water ice. This water abundance isn't just about having enough to drink. Water is perhaps the most versatile resource in space, serving as a source of oxygen for breathing, hydrogen for fuel, and radiation shielding when frozen. The electrolysis of water produces both the oxygen needed for life support and the hydrogen-oxygen combination that makes one of the most efficient rocket fuels available. A comet civilization would have access to unlimited quantities of this crucial resource without the need for complex extraction operations or competition with other uses. The organic chemistry of comets provides another resource advantage that planetary bodies generally lack. Comets contain complex organic compounds, including amino acids and other prebiotic molecules that could potentially be processed into food supplements, pharmaceuticals, or industrial chemicals. These organic resources could reduce the dependence on Earth-based supplies and provide the foundation for sophisticated chemical industries in space. The energy economics of comet settlements could be surprisingly favorable compared to other space colonization options. while comets spend long periods far from the Sun where solar energy is limited. They also spend portions of their orbits in the inner solar system, where solar energy is abundant. During these periods, massive solar arrays could be deployed to collect and store energy for use during the darker periods of the orbit. The predictable nature of comet orbits means that energy planning could be done decades in advance, allowing for sophisticated energy storage and management systems. Nuclear power systems on comets could actually be more efficient than on planetary bodies because of the excellent natural cooling provided by the space environment. The waste heat from nuclear reactors, which is a major engineering challenge on planets with atmospheres, can be easily radiated away in the vacuum of space. The abundant water ice on comets could also provide cooling and radiation shielding for nuclear power systems. The construction advantages of comet environments are often overlooked. The low gravity and porous structure of comets could actually make large-scale construction easier than on planetary bodies. Instead of fighting against strong gravity and solid bedrock, construction crews would be working with materials that can be easily carved, melted, and reshaped. The ice and organic compounds found in comets could potentially be processed into construction materials, reducing the need to transport building supplies from Earth. The underground construction possibilities on comets are particularly attractive. The ice provides natural radiation shielding while being easy to excavate with thermal tools. Unlike underground construction on Earth, which requires heavy machinery and explosive excavation techniques, comet excavation could be accomplished with relatively simple heating systems that sublimate the ice and capture the resulting water vapor for use. The scientific value of comet civilizations could be extraordinary, providing research opportunities that justify the investment in comet settlements independent of their value as human habitats. Comets are time capsules from the formation of the solar system, containing materials that have been preserved unchanged for 4.6 billion years. A permanent scientific presence on a comet would provide unprecedented access to these ancient materials and the opportunity to study them in their natural environment. The astronomical advantages of comet-based observatories could revolutionize our understanding of the universe. The natural motion of comets provides observation platforms at distances from Earth that would be extremely expensive to reach with conventional spacecraft. A telescope on a comet could achieve parallax measurements over baselines of billions of kilometers, enabling precise distance measurements to nearby stars and detailed studies of exoplanetary systems. The isolation and darkness of comet environments during their periods in the outer solar system would provide ideal conditions for sensitive astronomical observations. Radio telescopes on comets would be free from the electromagnetic interference that increasingly plagues Earth-based observations. Infrared telescopes would benefit from the natural cooling provided by the space environment. The lack of atmospheric interference would enable observations across the entire electromagnetic spectrum. The strategic military and economic implications of comet settlements could be significant, though hopefully peaceful. Mobile bases that can travel throughout the solar system would provide unprecedented flexibility for space operations. Comet settlements could serve as refueling stations, communication relays, or emergency shelters for spacecraft traveling to the outer solar system. The resources available on comets could supply space-based industries that would be impossible to establish on resource-poor bodies like the Moon. The backup civilization potential of comet settlements addresses one of the most serious long-term risks facing humanity. Unlike planetary settlements, which could potentially be vulnerable to the same catastrophic events that might threaten Earth, comet civilizations would be naturally isolated and mobile. A comet-based backup of human civilization would be constantly moving through space, making it unlikely that any single catastrophic event could threaten both Earth and all comet settlements simultaneously. The genetic and cultural preservation opportunities provided by comet settlements could be invaluable for maintaining human diversity. The isolation of comet communities would naturally preserve different genetic lineages and cultural traditions, preventing the homogenization that might occur in more connected planetary settlements. Over time, Different comet civilizations might develop distinct cultures and even biological adaptations that could enhance the overall resilience of human civilization. The economic opportunities for space-based industries could be greater on comets than on planetary bodies. The low-gravity environment would make it easy to launch processed materials to other destinations in the solar system. The abundant water and organic compounds could supply space-based manufacturing operations. The mobility of comets could bring these industrial operations close to markets throughout the solar system during different parts of their orbits. The mining potential of comets extends beyond their own resources to their role as mobile mining platforms. Comets often pass through asteroid-rich regions of the solar system, providing opportunities to survey and potentially capture asteroids for mining operations. The low gravity of comets would make it relatively easy to bring asteroid materials to the comet for processing and use. The communication advantages of comet networks could address one of the major challenges of space exploration and settlement. A network of comet-based communication relays could provide communication coverage throughout the solar system, enabling real-time coordination of space activities and maintaining contact with isolated settlements. The mobile nature of comets would allow communication networks to adapt to changing mission requirements and provide coverage to previously inaccessible regions. The transportation cost advantages of comet settlements could be substantial for certain types of space missions. Instead of launching everything from Earth's deep gravity well, missions to the outer solar system could use comet settlements as staging areas. The resources available on comets could supply spacecraft with fuel, water, and other consumables, dramatically reducing the mass that needs to be launched from Earth. The experimental value of comet settlements for testing space colonization technologies could inform all future space settlement efforts. The extreme challenges of comet environments would drive the development of life support systems, construction techniques, and social organizations that could be applied to settlements on Mars, asteroids, or other challenging environments. Comet settlements could serve as proving grounds for technologies and approaches that would be essential for human expansion throughout the solar system. The international cooperation opportunities presented by comet settlements could have benefits that extend far beyond space exploration. The enormous challenges and costs of establishing comet civilizations would virtually require international cooperation on an unprecedented scale. The shared goals and mutual dependence of comet operations could serve as models for international cooperation in addressing other global challenges such as climate change, resource management, and conflict resolution. The educational and inspirational value of comet settlements could motivate new generations of scientists, engineers, and explorers. The dramatic nature of living on wandering ice balls in space would capture public imagination in ways that could sustain long-term support for space exploration and scientific research. The real-time documentation of life on comets could provide educational content that makes science and space exploration accessible and exciting to people around the world. The technological spin-off benefits of comet settlement technology could have broad applications on Earth and in other space environments. The life support systems developed for comet habitats could improve environmental control systems for submarines, Antarctic stations, and other isolated facilities on Earth. The resource processing techniques developed for comets could be applied to terrestrial recycling and waste management. The construction methods developed for low-gravity environments could enable new types of structures and manufacturing processes. The long-term survival strategy advantages of comet settlements address the fundamental question of human survival in an uncertain universe. Planetary settlements, no matter how well established, remain vulnerable to catastrophic events that could affect entire worlds. Asteroid impacts, volcanic catastrophes, or other planetary disasters could potentially wipe out even well-established planetary colonies. Comet settlements, with their mobility and isolation, provide a form of insurance against such catastrophic risks. The philosophical and cultural advantages of comet settlements relate to fundamental questions about what it means to be human and how human civilization should develop. Living on comets would require levels of cooperation, technological sophistication, and environmental awareness that could drive positive changes in human culture and values. The experience of living as a truly spacefaring species could fundamentally alter how humans see themselves and their place in the universe. The competitive advantages of comet settlements in the emerging space economy could be substantial. As space-based industries develop and competition for resources and strategic positions intensifies, the mobility and resource advantages of comet settlements could provide significant competitive advantages. Comet-based operations could respond rapidly to changing market conditions and resource availability throughout the solar system. Despite all the challenges and risks involved, comet settlements offer unique advantages that could make them not just viable alternatives to planetary colonies, but potentially superior choices for certain types of human space settlement. The key is recognizing that comet settlements wouldn't replace planetary colonies, but would complement them, providing capabilities and opportunities that are impossible to achieve with fixed planetary bases. Given the realities, what's the final answer? After exploring every aspect of comet civilizations, from the technical challenges to the biological risks to the potential advantages, we arrive at the ultimate question that has driven this entire investigation. Could humans really build a permanent, sustainable civilization on a comet? The answer is both more complex and more hopeful than simple yes or no responses would suggest. From a purely technological perspective, building settlements on comets is not only possible, but achievable with extensions of current technology and engineering approaches that are already being developed for other space applications. We have successfully landed on comets, as demonstrated by the European Space Agency's Philae mission. We have the basic life support technologies needed to sustain humans in space environments, proven through decades of International Space Station operations. We understand the fundamental engineering principles needed for construction in low-gravity environments, radiation shielding, and closed-loop resource utilization. The key technological challenges of comet settlement, while extreme, are not fundamentally different from those being addressed for other space settlement scenarios. The artificial gravity systems needed for human health could use rotating habitat technology that is already being researched for Mars missions and space stations. The nuclear power systems needed for energy during Comet's journey through the outer solar system are variations of reactor designs already being developed for space applications. The life support and resource processing systems would be more complex versions of technologies already operating on the International Space Station. The construction techniques needed for comet settlements would require new approaches, but they build on established principles. The thermal excavation methods needed to carve habitats from comet ice are extensions of techniques already used for ice construction in Antarctica and for thermal drilling in various terrestrial applications. The materials science needed to work with processed comet materials would require research and development, but not breakthroughs in fundamental physics or chemistry. However, technological feasibility is only part of the equation for successful comet civilizations. The biological challenges of long-term human habitation in comet environments are substantial and not fully solved by current space medicine knowledge. The bone density loss, muscle atrophy, radiation exposure, and other health effects of long-duration space habitation remain serious concerns that would require either significant medical interventions or potential genetic adaptations over multiple generations. The artificial gravity systems that could address many of these biological challenges are technologically feasible, but would require massive engineering projects and substantial energy expenditure. Rotating habitats large enough to provide Earth-like gravity through centrifugal force would need to be enormous structures, potentially kilometers in diameter, built in the challenging environment of a comet's surface. The engineering and construction challenges of such projects would push human technological capabilities to their limits. The radiation protection requirements for comet settlements are achievable, but would impose significant constraints on habitat design and daily life. The natural ice of comets provides excellent radiation shielding, but inhabitants would need to spend most of their time in heavily shielded underground areas. Surface activities would be limited to periods when radiation levels are acceptable, potentially confining inhabitants to underground bunkers for years at a time during high radiation periods. The psychological and social challenges of comet civilizations represent perhaps the most uncertain aspects of their long-term viability. Humans have never attempted to maintain permanent settlements under conditions of complete isolation for periods measured in decades or centuries. The psychological stresses of living in artificial environments, dealing with constant environmental threats, and being cut off from the broader human community could have effects that are difficult to predict or prepare for. The social structures needed for comet civilizations would need to be fundamentally different from any human society that has ever existed. The small population size, complete isolation, and mutual dependence for survival would require new approaches to governance, conflict resolution, and social organization. The success or failure of these social experiments could determine whether comet settlements thrive or collapse regardless of their technological sophistication. The economic viability of comet settlements remains one of the most challenging aspects of the entire concept. The initial investment required to establish even a small comet settlement would be enormous, potentially exceeding the entire current global space budget by orders of magnitude. The return on investment would need to be calculated over timescales of centuries rather than years, making traditional economic analysis almost meaningless. However, the economic calculation becomes more favorable when considered as part of a broader space development strategy rather than as isolated projects. Comet settlements could serve multiple purposes simultaneously, functioning as scientific research stations, resource extraction operations, strategic outposts, and stepping stones for further space exploration. The value of these combined functions could potentially justify the enormous initial investment. The resource extraction potential of comets could provide economic returns that help offset the costs of settlement. The water, organic compounds, and minerals available on comets could supply space-based industries and other space settlements, creating economic value that doesn't depend on shipping materials back to Earth. As the space economy develops and demand for space-based resources grows, comet settlements could become economically viable as suppliers of essential materials. The scientific value of permanent comet settlements could provide returns that are difficult to quantify in purely economic terms, but could be invaluable for human knowledge and technological development. The research opportunities provided by direct access to pristine solar system materials, ideal astronomical observation conditions, and unique experimental environments could advance human understanding in ways that benefit all of civilization. The timeline for establishing comet civilizations would likely span multiple decades or centuries, with development occurring in carefully planned phases. The first phase would probably involve robotic surveys and sample return missions to identify suitable target comets and understand their characteristics in detail. This phase is already beginning with current and planned comet missions that are providing the basic knowledge needed for future human missions. The second phase would involve establishing temporary human outposts on selected comets, similar to the research stations currently operated in Antarctica. These outposts would test basic technologies and survival systems while conducting scientific research and resource extraction experiments. The duration of these missions would gradually increase as technologies improve and experience accumulates. The third phase would involve establishing permanent settlements with closed-loop life support systems and self-sufficient resource production. These settlements would still maintain connections with Earth and other space settlements, but would be capable of surviving independently for extended periods. The population of these settlements would gradually grow as experience demonstrates their viability and safety. The final phase would involve the development of truly self-sufficient comet civilizations that could survive and thrive independently of Earth-based support. These civilizations would have their own manufacturing capabilities, governance systems, and cultural traditions adapted to comet environments. They would serve as stepping stones for further human expansion into the outer solar system and potentially to other star systems. The site selection for comet settlements would be critical for their success. Not all comets would be suitable for human habitation, and careful analysis would be needed to identify targets with favorable characteristics. The ideal comet would have a relatively stable orbit that doesn't take it too close to the Sun during perihelion, abundant water and organic resources, a size large enough to support substantial construction projects, and a composition that allows for stable underground construction. Short-period comets with orbital periods of decades rather than centuries would probably be preferred for initial settlement attempts because they allow for more frequent communication and resupply opportunities with Earth. Comets with orbits that bring them relatively close to Earth during part of their cycle would be ideal for initial missions and ongoing support operations. The international cooperation required for comet settlement projects would be unprecedented in scope and duration. No single nation currently has the technological and economic resources needed to establish comet settlements independently. International cooperation would be essential not just for sharing costs and expertise, but also for providing the political stability and long-term commitment needed for projects that span multiple generations. The legal and governance frameworks for comet settlements would need to address questions that have never been faced in human history. Who owns a comet? What laws apply to settlements on objects that travel through the territories of multiple nations or beyond any national jurisdiction? How are conflicts resolved when the nearest authority is years away by communication? These questions would need to be addressed before serious comet settlement projects could begin. The risk management for comet settlements would need to address catastrophic scenarios that could threaten the survival of entire communities. Unlike terrestrial settlements, where help is usually available within hours or days, comet settlements would need to be prepared for emergencies that could last for years without external assistance. Backup systems, redundant equipment, and emergency protocols would need to be far more comprehensive than anything currently required for space missions. The success criteria for comet civilizations would need to be carefully defined to guide development and measure progress. Short-term success might be measured by the ability to maintain human life and conduct productive activities for periods of months or years. Medium-term success would involve achieving self-sufficiency in basic life support and resource production. Long-term success would require maintaining stable, growing communities that can thrive independently and contribute to broader human civilization. Despite all the challenges and uncertainties, the fundamental answer to whether humans could build civilizations on comets is yes, but with significant caveats. The technology needed for comet settlements is achievable with continued development of current space technologies. The biological challenges are serious, but potentially manageable with appropriate medical interventions and habitat design. The social and psychological challenges are largely unknown, but not necessarily insurmountable. The real question is not whether comet civilizations are possible, but whether they are desirable and worth the enormous investment required. The answer to that question depends on how we value scientific discovery, technological advancement, human expansion into space, and insurance against catastrophic risks to Earth-based civilization. Comet settlements would not be easy, comfortable, or safe by Earth standards. They would require people willing to accept extraordinary risks and hardships in exchange for the opportunity to pioneer new frontiers of human experience. The inhabitants would need to be highly skilled, psychologically resilient, and completely committed to the success of their communities. But for those willing to accept these challenges, Comet settlements could offer opportunities that are impossible to achieve anywhere else. They could provide front-row seats to the greatest scientific discoveries of our time, enable human expansion throughout the solar system, and ensure the long-term survival of human civilization. They could be the stepping stones that transform humanity from a single-planet species into a truly spacefaring civilization. The technical feasibility is there, the resources are available, the scientific value is enormous. The question is whether humanity has the vision, courage, and commitment needed to turn this incredible possibility into reality. Based on current consensus in astrobiology and space engineering circles, comet civilizations represent one of the most challenging but potentially rewarding frontiers for human expansion into space. Building a civilization on a comet isn't impossible, it's just incredibly challenging. Perhaps comets won't become permanent homes, but they could become stepping stones, science outposts, or way stations in humanity's future as we explore our solar neighborhood. As we reach the end of our journey through the possibilities and perils of comet civilizations, we find ourselves confronting one of the most audacious questions humanity has ever dared to ask. Could we really make our homes aboard these ancient wanderers, these cosmic snowballs that have been dancing through space since the birth of our solar system? The answer we've discovered is both humbling and inspiring. Building a civilization on a comet isn't impossible. It's just incredibly challenging in ways that push every boundary of human ingenuity, courage, and determination. We've seen that the technology exists or is within reach. We've explored how the abundant resources of comets could sustain human life. We've examined the revolutionary engineering solutions that could make permanent settlements viable, yet we've also confronted the harsh realities of radiation exposure, biological adaptation, social isolation, and psychological stresses that would test the limits of human resilience. What emerges from this analysis is not a simple roadmap to comet colonization, but rather a vision of what might be possible if humanity chooses to embrace one of the most extreme challenges our species has ever contemplated. Comet civilizations represent the far frontier of human ambition, a goal so demanding that achieving it would fundamentally transform what it means to be human. The scientific opportunities alone could justify the enormous effort required. Permanent access to 4.6 billion-year-old materials, astronomical observations from the outer solar system, and research conducted in environments that cannot be replicated anywhere else could revolutionize our understanding of the universe and our place within it. The technologies developed for comet habitation could drive innovations that benefit all of human civilization, from advanced life support systems to revolutionary construction techniques to breakthrough approaches to sustainable living. Perhaps most importantly, comet civilizations could serve as insurance policies for human survival, mobile arks that could preserve human knowledge, culture, and genetic diversity, even if catastrophic events threaten Earth-based civilization. In an uncertain universe where asteroid impacts, volcanic catastrophes, or other disasters could potentially end life on Earth, having self-sufficient human communities scattered throughout the solar system on mobile platforms could mean the difference between human extinction and human survival. The mobility of comet civilizations sets them apart from all other space settlement concepts. These wouldn't be static outposts locked into fixed locations, but traveling cities that could explore multiple destinations, serve as transportation hubs for further space exploration, and adapt to changing conditions and opportunities throughout the solar system. A network of comet settlements could transform humanity from a single-planet species into a truly spacefaring civilization, with the capability to thrive throughout the solar system and eventually beyond. Yet we must be honest about the costs and risks involved. Comet settlements would require international cooperation on a scale never before attempted, sustained commitment across multiple generations, and acceptance of risks that go far beyond anything humans have previously undertaken. The initial inhabitants would be pioneers in the truest sense, accepting extraordinary dangers and hardships for the chance to open new frontiers for human experience. The timeline for Comet civilizations stretches across decades or centuries, requiring patience and persistence that challenge our typically short-term thinking. The first robotic surveys and sample return missions are already underway with current Comet exploration programs. The establishment of temporary research outposts could occur within the next few decades if sufficient resources and political will can be mobilized. Permanent self-sufficient settlements would probably require most of the 21st century to achieve, with true Comet civilizations potentially emerging in the 22nd century or beyond. The selection of suitable target comets would be critical for success. Not every comet would be appropriate for human habitation, and extensive study would be needed to identify objects with favorable characteristics including stable orbits, abundant resources, suitable size, and structural integrity. The most promising candidates would probably be short-period comets with orbital cycles measured in decades rather than centuries, allowing for more practical communication and support from Earth-based operations. The social and cultural implications of comet civilizations are perhaps the most fascinating aspects of this entire concept. Communities living in complete isolation for extended periods would inevitably develop their own traditions, governance systems, and ways of life adapted to their unique environment. Over generations, comet inhabitants might become culturally and even biologically distinct from Earth-based humans, creating new branches of human civilization adapted to life among the stars. The economic justification for comet settlements becomes more compelling when viewed as part of a comprehensive space development strategy rather than isolated projects. The same infrastructure and technologies needed for comet habitation could support asteroid mining, outer planet exploration, and eventually interstellar missions. The resources extracted from comets could supply space-based industries and other settlements, creating economic value that helps justify the initial investment. The international cooperation required for comet settlements could have benefits that extend far beyond space exploration. Projects of this magnitude would require nations to work together in unprecedented ways, potentially serving as models for addressing other global challenges, such as climate change, resource management, and conflict prevention. The shared goals and mutual dependence of comet operations could help build the international institutions and cooperation mechanisms needed for humanity's long-term survival and prosperity. The educational and inspirational value of comet settlement programs could motivate new generations of scientists, engineers, and explorers while capturing public imagination in ways that sustain long-term support for space exploration and scientific research. The dramatic nature of living on wandering ice balls in space would provide compelling narratives that make science and exploration accessible and exciting to people around the world. As we look toward the future, comet civilizations represent one possible path for human expansion into space, complementing rather than replacing other settlement concepts such as Mars colonies, lunar bases, and asteroid mining operations. Each approach offers unique advantages and faces distinct challenges, and the most successful space development strategy would probably include multiple types of settlements working together to establish human presence throughout the solar system. The fundamental question is not whether comet civilizations are technically possible, because the evidence suggests they are. The real question is whether humanity has the vision, courage, and commitment needed to undertake such an ambitious project. The answer to that question will depend on how we balance the enormous challenges against the potentially transformative benefits, and whether we're willing to invest in projects that span multiple generations and push the boundaries of human capability. Comet civilizations might never become the primary focus of human space settlement efforts, but they could serve as crucial components of a broader strategy for human survival and expansion. They could be the research stations that unlock the secrets of the early solar system, the stepping stones that enable exploration of the outer planets, the mobile platforms that extend human reach throughout the cosmos, and the backup systems that ensure human civilization survives whatever challenges the future might bring. Perhaps comets won't become permanent homes for millions of people, but they could become specialized outposts for thousands of dedicated researchers, explorers, and pioneers. They could be the scientific stations that advance human knowledge, the resource extraction operations that supply space-based industries, the communication relays that connect far-flung human settlements, and the emergency shelters that provide refuge for travelers in the depths of space. The story of comet civilizations is ultimately a story about human potential and the choices we make about our future as a species. It challenges us to think beyond the comfortable confines of our home planet and consider what might be possible if we dare to embrace the vast cosmos that surrounds us. It asks whether we're content to remain forever bound to Earth, or whether we have the courage to become citizens of the solar system and eventually the galaxy. The cosmos is vast, ancient, and full of wonders we're only beginning to understand. Comets have been journeying through this cosmic ocean for billions of years, carrying with them the raw materials and energy sources that could sustain human civilization far from the warmth of our sun. Whether we choose to climb aboard these wandering worlds and join their eternal dance through space will depend on how boldly we're willing to dream and how hard we're willing to work to turn those dreams into reality. The universe is waiting. The comets are out there, following their ancient paths through the darkness between worlds. The question is whether humanity is ready to take the next great step in our species' incredible journey among the stars.